Okay, so welcome everybody for the third and last day of SYSTOR. I hope and think we will have at least as interesting a day as we had in the previous 2 days. I remind you that we have now the first session, and then we have highlight papers, and we finish with the third keynote, and then some closing remark by the committee. So thanks again for joining, and let's move to Aishwarya for the chair who's chairing the first session. Please take the stand. We don't have a stand, but.
Hi, everyone. I'm happy to be here and I'm excited to be here. I'm Aishwarya and I recently graduated from the University of Wisconsin-Madison and currently a postdoc at VMware Research. So today I'll be chairing session 6, which is NVM part 2, and we have 2 wonderful papers in this session. So first up in this session, we have Jinfeng, who is a 6th-year PhD student from the University of Minnesota Twin Cities, majoring in electrical engineering. Jinfeng is interested in emerging storage technologies such as NVMs and databases and machine learning for storage, and is currently looking for jobs. So if anyone is interested in talking to Jinfeng, please do so. And today we'll talk about Heuristic DB, a hybrid database storage database system using a non-volatile memory block device. Let's hear the talk.
Hello everyone, my name is Jinfeng, a PhD student from University of Minnesota. Today I will present my research project called Heuristic DB, a hybrid storage database system using NVM block device. At the beginning of this presentation, I will explain the background and motivations of our research. The system design and performance evaluation are discussed next. We draw a conclusion in the last section. The NVM is an emerging storage technology. It serves as either a main memory, known as NVDIMM, or persistent storage, known as NVM block device. The NVM block device has several advantages. First, compared with NetSSD, the NVM block device provides much higher read-write bandwidth. Second, compared with NVDIMM, NVM block device can be directly operated without requiring any hardware updates. Considering those performance advantages, in this project, we use NVM block device as a block cache for hybrid database system. Building a hybrid storage system that using a high-performance storage device as a block cache for conventional storage usually is the most cost-efficient way to improve database system performance. Several reasons motivated us to develop a new hybrid algorithm. First, prior hybrid algorithms are built on the NetSSD and HDD architecture, which is not fit the characteristics of NVM block device. Second, without considering the characteristics of database block request, prior works have low cache hit ratio and suffers of severe performance degradation as the access pattern of a workload changed. In order to propose a perfect hybrid cache algorithm, we studied the characteristics of database block request from the following 2 aspects, including data types and access behaviors. The data types we studied is table, index, and page. During query processing, the access pattern of each required table or index is determined and has 3 possibilities, as the left figure shows. And those possibilities include: first, sequential access. When no index is used for a query, the database engine scans the target table sequentially. Second, random access. When an index is provided, both index and tables are accessed randomly. Third, repeated access. When multiple operators access a table or index during a query, some pages inside that table or index are accessed repeatedly. This study aims to leverage the NVM block device as an extension of database buffer pool to boost database performance. By considering the characteristics of database block request and the performance behaviors of NVM block device, the goal is approached from the following 3 directions. First, guarantee reusability. In a hybrid system, a performance gain only can be delivered when a cache hit occurs. Thus, it is necessary to prioritize tables indexed based on their reuse possibility. Second, adaptive demotion or eviction is required. Because access patterns and required tables of each query are different, it is reasonable to adaptively adjust the priorities of database tables, index, and cached pages before running a new query. Third, the benefit of caching a page in the NVM block device. Because NVM provides much higher read-write bandwidth than conventional storage, hence, it is preferable to cache all block requests with high range of possibilities in the NVM to deliver performance gains. Based on the design principles discussed above, a set of heuristic rules for a single query is presented in this section, and the heuristic rules for concurrent queries are provided in the later section. For Rule 1, when a table is accessed sequentially, all pages inside that table are only accessed once, thus we do not cache the pages belong to it. For Rule 2, when a table or index is randomly accessed, only a tiny portion of matched pages are accessed, and the cache pollution issues caused by omitting those pages are limited. On the contrary, those pages can deliver performance benefit once they are reused in the subsequent queries. Thus, it is preferable to omit the pages belong to that table or index. Rule 3. When multiple operators access a table or index, some pages inside that table or index will be accessed more than once. Thus, it is preferable to omit the pages from that table or index. In addition, to guarantee the pages inside the NVM buffer pool are the most profitable ones, a cache replacement happens unless its temperature is higher than the coldest one in the NVM buffer pool. For a write request, considering the unprecedented write performance of NVM block device, all write requests are buffered in the NVM buffer pool and flushed into the storage later if needed. For Rule 6, since the tables or index required and the access behaviors of each table or index varying as queries change, to admit incoming hot pages to deliver performance acceleration, a demotion or eviction of cached pages is required when a new query is submitted. An eviction action is taken if no performance benefit is provided in the past, and if there is a table or index required by both previous and newly submitted queries. Otherwise, a demotion is taken. From the storage leader's perspective, the block-level characteristics of concurrent queries are similar to the single ones. Hence, the priority assignment rules for concurrent queries is much like those used in the single query execution. More details are: when a query is submitted while one or more other queries are still running, a priority adjustment of cached pages is required. The detailed criteria are the same as in Rule 6. In addition, the access behaviors of a table or index may change after a new query is submitted. Hence, an access behavior verification is required for all tables and indexes required by concurrent queries. Finally, when multiple queries run concurrently, the quality of service for database block request follows Rules 1 to 5. To implement the proposed rules, for assistant programs including a querying profile queue, an eviction demotion program, a table access parting detector, and page placement controller are developed. The querying profile queue is developed to analyze the profiles of the past and newly submitted queries and send either an eviction or a demotion request to the system. According to Rules 6 and 7, the size of the queue equals to 2. Each item in the queue contains two types of variables: a table linked list, which is used to record the tables or indexes required by the corresponding query, and a performance variable, which is used to record the number of hits since a query has run. Whenever a query is submitted, its profile information is inserted into the rear of the queue. Then, the previous query's profile information is extracted. If the number of hits of previous query is 0, and there exists a table or index required by both previous and newly submitted query, an eviction request is generated. Otherwise, a demotion request is generated. To distinguish the access frequency of each cached page, a LFU data structure is used. The pages have the same access frequency and assigned into the same linked list. To perform an eviction request, we reset the access frequency of all cached pages to 0. The details are: we scan all linked lists from the lowest access frequency to the highest one in sequence, and insert every linked list into the most recently used place of the number 0 linked list. This design enables heuristic DB to replace more easily pages that were hard in the past but are rarely accessed in the newly submitted queries. For demotion requests, the EV program performs the similar operations as for an eviction request. The only difference is it inserts all cached pages into the number 1 linked list. The table access parsing detector is used to detect the access behaviors of each required table or index during query. A table is concluded to be sequentially accessed if its corresponding sequential ratio is higher than 90%, otherwise it is randomly accessed. Well, the sequential ratio is defined as the number of pages accessed by database read ahead mechanism divided by the total number of accessed pages. To minimize the detection overhead, we only monitor the first 1% accessed pages. We conclude a table or index is repeatedly accessed if the access frequency of a page from it is greater than 1. The page placement controller is used to redirect a request into either NVM buffer pool or storage, following heuristic rules 1 to 5. When a cache miss occurs, a page placement happens only if the access behaviors of the table or index to which this page belonged is not sequential, and if the access frequency of the required page is higher than the minimum access frequency of cache pages. To evaluate the effectiveness of proposed design, a trace-based evaluation is conducted at first using TPCE and TPCH benchmark. The database size of each benchmark is set to 90 GB and 97 GB respectively. The NVM buffer pool size is set to 10 to 60 GB. 3 workloads, including a complex online analytical process workload, TPCH workload, and TPCE workload, are used for testing. We use LRU, MRU, LFU, multi-queue, ARC, and TEC as baseline for comparison. Two metrics, including the cache ratio and data migration size between NVM buffer pool and storage, are employed to evaluate the effectiveness of test algorithms. From the result, HeuristicDB outperforms all tested baselines on both cache ratio and data migration size. It delivers up to 10% higher cache ratio and migrates 3.6 less data between storage and NVM buffer pool compared with the second-best algorithm. We also implemented HeuristicDB on the real system. In the experiment, MySQL runs on the top of the system. We use OptiSSD as the NVM block device, and NetSSD acts as a conventional storage device. The same workload are employed for performance evaluation. Two baseline algorithms are used for comparison, and they are LRU and the TAC algorithm. From the result, HeuristicDB delivers highest performance speedup compared with other two baselines. For instance, for complex OLAP workload, HeuristicDB improves database performance over LRU and TAC by up to 25% when the NVM buffer pool size set to 30 GB. Similar results can also be observed from TPCH and TPCE workload. We also quantify the overhead of HeuristicDB. The experimental results show that the actual memory space consumed by the HeuristicDB for storing the metadata of TPCH and TPCE is only 57 MB and 61 MB respectively. Compared with capacities of host memory, the footprint of HeuristicDB is minimal. In addition, the actual time spent by the querying profile queue and the EV program of HeuristicDB for each query or transaction is only 0.5 to 2% of their corresponding execution time. This low overhead is because those programs are run only at the beginning of the query and are completed quickly. As a result, the computation overhead of HeuristicDB is trivial. Compared with OLTP workload, an OLAP query has higher complexity and requires many more block requests. Therefore, in most cases, the I/O time is a main bottleneck for OLAP queries. This subsection describes the detailed internals of OLAP workload. The speedup achieved by the HeuristicDB and other two baselines on each query is plotted in the figure. In the experiment, the NVM buffer pool is set to 30 GB. From the result, the HeuristicDB delivers the highest performance acceleration for almost all queries inside both the complex OLAP and the TPCH workload. The performance advantages of HeuristicDB can be attributed into two design principles. First, by considering the characteristics of database block requests, the tables and indexes required by the query are prioritized based on their usability. This enables heuristic DB to cache the most profitable pages in the NVM buffer pool to deliver maximum performance gains with less data migration in the querying execution. Second, the adaptive EV program enables heuristic DB to evict out-demote cached pages and admit new incoming hard pages more efficiently as the access pattern of a workload changed. In this work, we propose a heuristic DB, a hybrid storage database system using NVM block device. By considering the characteristics of database block request, heuristic DB outperforms prior works on both cache hit ratio and data migration size on both OLAP and OLTP workload. Most significantly, it delivers up to 75% higher performance compared with test baselines. Here is a reference used in this presentation and the QA section, and we can discuss more if you have any questions about this project. Hello.
Hi. So thank you for the great talk. So if you have any questions, please do post on Slack, or also please raise your hand in Zoom so that you can ask the question directly here.
Yes, I'm happy to take a question now.
Yeah. So while we are waiting on questions over Slack, I have a question for you. So did you consider using NVM as a persistent memory instead of a block device? And what in your setup made NVM more suitable to be used as a block device than as NVDIM, for example?
Okay, thanks for your question. So in this example, I did not use NVM as a persistent storage. So I just directly use it as a block cache. As I mentioned earlier in this presentation, so in this project, we use the NVM block device instead of the NVM. So these two devices have some difference. So NVM is like a conventional like memory DIMM. You can directly plug in that into the memory DIMM. And it can directly communicate with the host CPU by the memory bus. But the NVM block device is kind of the block device, but the cells in that NVM block device is actually like a 3DS point memory, a kind of the NVM. Mm-hmm. So that's the difference. And also the NVM block device still communicate with hosts through the PCIe interface. So that's the most significant difference. And the problem for the NVM device is it will suffer some severe performance degradation while the number of threads increase. But however, for the NVM block device, it didn't suffer this issue. So consider this performance disadvantages of NVM. So in our project, we use NVM block device instead of the NVM.
Okay. So I have one more question for you.
Mm-hmm.
So you presented many heuristic rules, right?
Yes.
So I was wondering, like, what among those rules are specific to NVM, and like what among those rules are applicable to, let's say, any storage hierarchy, like where you have a slow device and a fast device?
Oh, so actually, those rules is only designed for the database, for the relational database. So like, so we actually characteristics the database. We study the characteristics of database block requests at first, and we find some specific characteristics of database block request, and then based on those characteristics, we designed and proposed some rules, and those rules is only applied for the database.
So let's say you have the database, right? And let's say you have the database deployed on a different hierarchy, like NAND-based SSD on top of HDDs, like where the SSD is the faster device and the HDD is the slower device. So what among those rules that you have sort of described in this paper are applicable to such a hierarchy as well?
So I think maybe if you change the storage device, for instance, you decide that in the low storage, in the low performance storage device, we use HDD, and the high performance storage, we use SSD. Maybe our rules will not our heuristic DB will not work well in such a hybrid architecture. This is because, for instance, the conventional NetSSD may provide a similar sequential read performance as HDD, right?
Mm-hmm.
So that means cache the sequential read request will not give you any performance benefit. So, but in our case, we use the NVM block device as a block cache. So it provides much higher sequential read and random read performance compared with all conventional storage devices such as NetSSD and HDD. And we prefer to cache the sequential read if that table is accessed multiple times. So it will guarantee. So in such combination, it will guarantee that we can gain some performance gains even for the sequential read request. But on the contrary, for the other combination, like you said, the NetSSD plus HDD, our heuristic DB will not provide performance gains since the NetSSD provides similar sequential read performance as HDD. Yeah.
Thank you for answering these questions. So if anyone else, if you have like any other questions for this talk, please post on the Slack channel. So thank you so much. So let's now move on to the next talk. So for the next talk, we have Mikhail, who's a doctoral candidate, a fourth-year PhD student at Dresden Database Research Group at Technical University Dresden, Germany. Mikhail is interested in hybrid memory or NVRAM-centric database systems and is in their fourth year of PhD studies and should be defending soon. So today we'll hear about SIMD MIMD cocktail in a hybrid memory class, shaken, not stirred. So let's hear the talk.
Hello, ladies and gentlemen. My name is Mikhail Zarubin from Technical University Dresden. I'm presenting a paper with the title SIMD MIMD cocktail in a hybrid memory glass, shaken, not stirred. First of all, I would like to introduce the use case and targeted systems. So we rely our work on analytical data processing systems as their importance is constantly increasing. This happens due to the ubiquitous digitization throughout all aspects of social life. So the amounts of stored and processed data are ever growing. Such analytical systems impose two major requirements. First requirement is responsiveness. So it is expected that data processing is done in an interactive way, like it happens in online dashboards. And the second requirement is parallelism. It is expected that such systems are accessed by multiple concurrent clients simultaneously. That is perfectly true also for online shops. Such analytical data processing systems work on the columnar data format and use it for data processing. That means that all values independently of the actual data type are mapped to the sequences of integers. Then these sequences are placed in byte addressable memory. That's also known as a memory processing paradigm. And finally, to obtain analytical results, the queries are expected to be executed over such columns. And the query here is the sequence of elementary operators, while most systems follow the operator at a time execution model. Let's have a look at a simple example on the right. So assume our client sent a query in the form of a SQL request. This query is translated into a query execution plan that represents the sequence of elementary operators. And finally, this sequence is executed by our computational cores. To provide support for parallelism, modern data analytical systems rely on multiple instruction, multiple data paradigm. There are two major flavors typically deployed in such systems. First one is intra-operator parallelism, and here all the data columns are partitioned into chunks, and every chunk is processed by its specific thread. The second approach is called inter-query parallelism. Here, the complete query is encapsulated by the specifically devoted MIMD thread. We rely our research on this inter-query approach as it naturally fits for the multiple client concurrent execution. So this sequence of operator then is executed by a specific thread. Further, such threads could work on independent columns or on shared columns like with column C. And many systems use batching in order to exploit the special cache locality principle. That means that they batch queries and start them simultaneously. Okay, so now it's clear where the MIMD component of our cocktail comes from. Let's have a look at the origins of SIMD ingredient. SIMD, or single instruction multiple data, is a state-of-the-art optimization in analytical processing as well. And its goal is actually to increase the single thread performance and therefore to satisfy requirement A for responsiveness. State-of-the-art suggests to use largest available registers as they are able to accommodate more data within single instruction. Now we are coming to the challenge that we are tackling in this paper. So we just saw that both SIMD and MIMD are indispensable to achieve the highest performance in analytics, and both are well known. However, their interplay hasn't been investigated much so far. This challenge becomes even more interesting when considering hybrid memory systems that are equipped with DRAM and NVRAM. So the database is able to place the data to these two types of byte addressable memory and directly apply vectorized instructions on these memory regions. Therefore, our research goal is to enable superior combination of SIMD-MIMD on such hybrid memory systems. And to reach that goal, we follow through two steps. First, we provide extensive experimental analysis of typical behavior of the database operators. And second, we propose an optimization design that allows to select best suitable SIMD option at runtime. So let's proceed with step one. Here I will stop by just by a single example for brevity, namely for aggregation operator that performs a scan over the column and sum it up. So the chart on the left depicts the DRAM case. Here we show the throughput obtained from all the threads in terms of runs per second as axis Y, and the thread counts are shown on the bottom axis. Here we see that for small and moderate concurrency levels, the large registers give the best performance. That's rather expected behavior. However, starting from 18 threads, we see that the smaller register starts to outperform. So AVX 502 is better than 512, and scalar is the best. And this situation is preserved until the full occupancy level, where the scalar case is able to outperform AVX 512 by around 50%. What happens on NVRAM? So here, first of all, we see that the general level of performance is lower. That is, however, expected due to the lower NVRAM performance. The other important observation here that the domination of large registers is actually preserved for most concurrency level, and only at full occupancy the difference between SIMD flavors is disappearing. Therefore, we make the following outcomes here: that DRAM prefers small registers for high concurrency level, while on VRAM, large registers dominate at most levels. Here I will just sum up lessons learned from our all micro benchmarks and present most interesting outcomes. First of all, we've shown that SIMD greatly improves performance on both DRAM and NVRAM compared to scalar execution. However, large SIMD registers do not always yield the best performance, and naive strategy of selecting always AVX 512 may be even harmful compared to scalar case. Best SIMD option depends on the memory type, concurrency level, and access pattern or operator. And furthermore, even subclasses of instructions may matter. For example, we saw that streaming, non-streaming flavors can differ a lot in performance for write-intensive workloads. However, there are more unexplored degrees of freedom. So far, we varied memory type, SIMD flavor, and concurrency levels. However, now we have an idea to shake distinct available SIMD flavors within same concurrent environment. Like, for example, we can run simultaneously AVX2 and AVX 112. The motivation that it could possibly mitigate the downclocking problem, that's an issue that appears when high number of threads accessing large registers, leading to the throttling of the CPU cores. Here we also suggest to deploy various shaking styles. So the first option we propose is the round robin option. That's rather easy to explain. Here we allocate the threads one by one. So the thread number, this is the core number 1 using AVX 2, and then 512, and so on. The second option, which we call sliced cocktail, is ratio-based. Here we fill the course enumerated from 1 till certain number with one flavor, and the remaining are filled with another flavor. There potentially could be more than 2 flavors. Okay, let's have a look how it does behave. Again, I will just start by an aggregation example. And here we start with the results we already saw. Here we use pattern-filled bars for such homogeneous scheme, while the round-robin schemes use the tilde sign here in between. So I will explain it based on the blue bar that mixes scalar with AVX 512. So here we basically distribute SIMD flavors evenly over the course. The most notable outcome of this experiment is that at all concurrency levels, there are certain options of the round-robin mixture that is able to overcome the base homogeneous schemes. So the homogeneous schemes always can be outperformed. Let's have a look on the second option. Here we deploy the sliced cocktail style. I will explain it with the orange bar. So the scalar to AVX 512 allocation. Here we fill course with numbers from 1 to 18 with scalar case, and then from 19 till the n we fill with AVX 512. And we saw that the performance delivered that way can greatly outperform the basic allocation. Like the orange bar is twice as high throughput as compared to AVX 512 pure scheme. And again, we see that for other concurrency levels, it's also there are schemes that outperform all basic schemes. However, there is no single best one. So here we have the green one is the best, and here the brown one is the best. So, therefore, we make the following outcomes. So SMD combinations may greatly outperform basic schemes, and it really matters how we shake such a cocktail. Okay, so after having these findings, we decided to deploy them for optimization purposes. Therefore, we extended the traditional approach with several components that allows the deployment of these newly revealed effects. First of all, at calibration phase, we suggested we collect the profiles of elementary database operators for the variety of SIMD options. Then at online time, we perform the selection or decision-making based on the dominating operator within query in order to vectorize it in the most optimal way. And then we use profiles for that and online information. And then finally, we allocate respective SIMD flavors over the course and access either DRAM or NVRAM data. Let's have a little bit deeper look on how it is implemented. Profiles follow the tabular format. So such a table is expected to tell us how we should allocate our SIMD operators over the course. So here we use a scalar case for course from 1 to 18 and AVX 112 for course from 19 to 24. That is obtained per such a combination on top. Then we also expect that there is a precompiled library of meaningful SIMD vectorized operators. So it's only required to implement a single SIMD version, then it could be specialized automatically, as shown by recent research. Having that, at online, we are able to perform online switch for dominating operator as it gives the highest impact on the overall throughput. For that, we use a lookup formula that imposes only negligible overhead. So it takes several parameters about the current workload. They are extracted from the batch. And finally, we found out which profile we should use to actually specify the SMD versions to be allocated over the course. Okay, after that, we performed an evaluation. We did it for elementary database operators, and here we just stop by with a more complex query based on aggregation. So the chart on the left depicts DRAM case. Here, the green arrow shows the best reachable performance, and the red arrow shows the chosen by our model approach. We see that in most cases, we are able to suggest the best option And in case if it's not suggested, the suggested case is just a few percent worse than the best. On NVRAM, the situation is a little bit worse in terms of correlation. So it's not always suggested the best case. However, due to the fact that the general diversity in performance is lower here, again, we lose only a few percent of possible performance that is undergained. Therefore, we make an inference here that our optimization delivers optimal or only just slightly suboptimal performance. What about the cost of our optimization? At calibration phase, we would need several hours to collect profiles, and that will occupy several kilobytes of memory. Then at optimization phase, we would need to spend some within microseconds of runtime to actually perform our online switch. However, that is completely amortized. And at execution time, we will be able to get up to 2 times speed up. So with that, I would like to conclude my talk and indicate the most important results. So we've shown that SIMD-MIMD interplay is an important way to optimize analytical data processing, as it is able to improve both responsiveness and throughput of the analytical data processing system. However, the largest registers do not always yield best performance here. While adaptive cocktailing may deliver up to 2 times speed up. However, in order to enable such speed ups, it's important to smartly select between available SIMD versions, and such a choice depends on memory type, concurrency level, and operator or access pattern. To automate this selection, we proposed the adaptive cocktail optimization design that imposes mostly negligible costs and suggests either optimal or only slightly suboptimal solution at runtime. For further details, I invite you to read the paper, and now thank you very much for your attention.
Hi, thank you so much for the interesting talk, and I found the title to be very interesting. So let's see if we have questions on Slack. So we don't have any questions yet. So while we are waiting for questions, I have a question for you. So do you have more insights into why with higher number of threads, the performance decreases for DRAM while for larger registers, while it did not for NVRAM?
Yeah, so our assumption here is that NVRAM is still lower than DRAM, and this effect is actually tightly coupled with the caching subsystems. And the caching replacement and trashing happens much faster for DRAM. Therefore, that can so the registers may become the bottleneck. While on NVRAM, the cache system is still waiting until the NVRAM respawns, and therefore the large registers do not have enough time to become a bottleneck, actually. So that's actually, yeah, the consequences of lower NVRAM performance.
Okay, great. So since I think I have like another question before we look for more questions on Slack. So since you require a profile like for queries, how does your system handle new queries that it hasn't seen before?
Yeah, so basically we target profiling for just elementary database operators and not for complete queries. Okay. Having such elementary profiles, we apply the optimal scheme for the complete query, because then the most the terminate operator is vectorized in the most optimal way, and therefore we are able to optimize this crucial part of the query. Because having the profiles for arbitrary queries would just explode the amount of profiles.
Yeah.
We anyway have to limit that.
Yeah, that's interesting. Yeah. So we have one question from Joel. I'm going to promote you as a panelist. Feel free to ask the question directly.
Hi, thanks. It's an interesting talk. I'm going to ask a question that's slightly off topic though. I'm curious to know if you or anybody in your team has been looking at processing in memory, because it adds like a new dimension to the kind of details that you're looking at.
So you mean like in-memory processing as in-memory database styles?
That's right.
Yeah,
you
sure.
Actually do some of these operations that you're talking about, but rather than doing it from the host CPU to process the data in memory.
Yeah, basically we rely here on near memory processing paradigm. So we do not have any data stored on the SSD or HDD, and all the processing happens in like in memory traditional way here. So we grab data from byte addressable memory, have it in cache, and then apply the operators through the CPU registers, either scalar or vectorized. So maybe I don't understand the question completely. Could you please then?
So you're headed in the right direction, just that there are new memory technologies that you can do the processing inside the DRAM.
Yeah, sure. We also think that that could work for MC DRAM, for example, for on-chip DRAM as well.
Okay, yeah, so it's something you're interested in, but haven't really looked into deeply yet.
Yeah, sorry. So here we just provide experience for NVRAM and DRAM, but yeah, our approach potentially can deploy with other memory types which are byte addressable. Yeah.
Cool. Thanks.
So I guess we don't have any more questions on Slack. So thank you so much for answering all these questions and the great talk. If you have more questions, please feel free to post on Slack, and I guess the authors would be more than happy to answer those questions offline. So now we would have a short 5-minute break followed by session 7, which is consisting of many highlight papers from different conferences. Thank you. Thank you all.
All right, I think it's time. Hi, everyone. I'm Ram. I'll be the session chair for this session. This is the highlights session where we have 5 interesting papers from, these are not original, these are not sister papers, but these are papers that were presented elsewhere. Now they're being represented here at Sister 21. So we have 5 papers, as I mentioned. The first one is EventDB, optimizing key value storage for spatial locality. Iran is going to tell us about this paper. Iran is a senior research engineer at Yahoo Research, where he works on distributed big data systems. And Iran holds a PhD from the Technion. Can we have the video play, please?
Hi, I'm Gilad from Yahoo Research here. Now representing a work on EventDB, a key value store optimized for spatial locality. So key value stores provide a simple abstraction mapping keys to values. They provide single key operations such as put, get, and delete, as well as occasionally range query operations, also known as scan, that return keys and values within a given range of keys. Key value stores need to deal with different workloads. Occasionally, those workloads are skewed. Namely, some keys are hotter or more popular in terms of reads, writes, scan, or all of the above. And for example, in this case, K6 is going to be more popular than K7. Now, in some cases, locality is exhibited not at the granularity of a single key, but rather at a complete range of keys. And this is what we call spatial locality. And this is common when keys are not just, do not contain just a single value or property, rather are composed of multiple properties. For example, this is what you get when you combine different fields or concatenate them and create a single key from them. And the benefit of using composite keys is that it allows the user to get a value based on multiple properties, which bypasses the limitation of a single index that's built in key value store. So let's look at a specific example. One of our internal production systems stores mobile application events, which include the application name, timestamp, and other kinds of data. 1% of those applications, namely the most popular ones, contribute 94% of the events. Now, if you wanted to be able to analyze the events such that we can get the events that happened in a certain application over the last, say, minute, then we can store the data using composite keys such that the prefix is the application name and the suffix is the timestamp. And in this case, what we'll get is that 1% of the ranges is going to contribute 94% of the events. The most popular design of key value stores is called LSM trees. In LSM trees, the most recent updates are stored in memory in a data structure called a memtable. And the rest of the keys and values are stored in several levels of files on disk. Now, those levels are in increasing size, in a factor of about 10 times larger, and their ranges overlap. From time to time, when a level gets full or passes a certain threshold, a compaction procedure kicks in, and the content of that level is merged into the level below it. So LSM trees storage is driven by writes. Namely, the most up-to-date writes are stored at the top in memory or at the top levels. And over time, writes propagate to the lower levels. So compactions merge potentially hot and cold ranges if we look at the read side. Namely, reads does not affect the location of the data, and hot keys might reach the lower levels. Further, since all levels cover the complete key range, namely overlap. When searching for a certain range of keys from the scan, we have to traverse all the levels in multiple files, since the keys included in that range might be spread across all those files and levels. EvenDB is an ordered key value store that is persistent and offers fast recovery. It provides atomic operations, including scans, and it's optimized for spatial locality. It also offers low write amplification. EvenDB relies on chunk-based organization, where chunks are much bigger than blocks, which are typically operating system pages, and also much smaller than common database shards, which are really large. So chunks are the basic unit for disk operation, including compactions, as well as memory caching and concurrency control. Chunk metadata is stored in memory as a linked list of chunk objects. Each chunk object holds metadata such as versions, synchronization mechanism, file handlers, and so on. And once a chunk passes the size limitation, it is just split. Now, in order to be able to reach the chunk that potentially contains the key we're interested in, we hold an index over all those chunks. Now, each chunk has its own storage we call func. That storage includes a log or a WAL, as well as an SS table, which is a sorted file that allows quick search. When we store a key in a certain chunk, that key is immediately stored within the log for persistent, and that log is occasionally merged into the SST in a procedure we call rebalance. Now, when we search a key that exists in a certain func, then we first search a row cache, which is a cache that stores particular hot keys. And then we search the log after going through the Bloom filters that are stored in memory. And lastly, we search the SST. And scans always search both the SST and the log because the keys might exist in both. Now, certain chunks might be very popular or very hot, in which case we'll create a memory caching we call a monk. A monk stores the complete key range within that, that's also stored in the SS table and the log, namely all the keys and values that are stored within that chunk. So when we store a key or update a key in a certain chunk, then that key is first stored in the log with its value, again, for persistence, and then it is stored in the monk. Occasionally, we rebalance the monk, which means we get rid of obsolete data and better arrange it for fast lookup. And rarely, we flush the monk to disk and create a new SS table. And this is just required in order to be able to flush the log and clear the log. Since the SS table is on disk, once we persist the data in the SS table, we can get rid of the log. Other than that, once we have a monk for a certain chunk, we never search the log, so we don't care if it grows infinitely, but that log occupies disk space, so we want to down the amount of space that it occupies. So when we search chunks that have a monk, we simply search the monk itself. It's a memory component, and we don't need to do anything else. And just to make something clear, monks are better suited for storing chunks which have many keys that are hot, which is typical to hot ranges. And this is as opposed to chunks that have single keys that are hot, in which case we better reserve the memory space and store that key in the raw cache. So our evaluation of EvenDB included 3 benchmark suites. First, we used the traces from an internal production system, storing 1/4 of a terabyte. Next, we used standard YCSB benchmarks, which includes simple keys. And lastly, we used an extended YCSB benchmark, which included composite keys, which we synthetically create using YCSB. And our state-of-the-art LSM is RocksDB. So the first benchmark is ingestion, namely storing the complete data set of 1/4 of a terabyte. And the graph shown here is a throughput timeline. Namely, it demonstrates the throughput of each database over time. And here, EvenDB is the blue line, and RocksDB is the dotted red line. What we can see here is that EvenDB maintains a much higher ingestion throughput, and therefore completes the workload 4 times faster, and also has a 4 times lower write amplification. One of the reasons EvenDB outperforms RocksDB can be seen when looking at the space amplification during the ingestion benchmark. The space amplification is basically the ratio between the amount of input generated by the application and the size of the database on disk. And in this case, we can see that RocksDB size grows significantly and then shrinks in a chainsaw pattern. And when that chainsaw drops, this means that compaction kicks in, and RocksDB uses a lot of resources to perform this compaction. And during that time, we can see on the throughput timeline on the right that the throughput indeed drops. EvenDB, on the other hand, it runs much more smoother, and compactions are done much more locally in the background without having a significant effect on throughput. And what we can also see is that most of the write amplification in EvenDB comes from the log space, which is the dotted line below. And this is mostly because we just don't care that the chunks that have monks, their logs grow because that does not affect us, the search performance. So EvenDB's advantages are first in-memory compactions, namely once a chunk gets hot, then it will have a monk, and that monk will observe most of the writes, and occasionally just write them back to disk to the SSD. And we also have localized compactions, namely when a chunk does not have a monk, then the compactions in which the log is merged into the SSD are local, namely they cover a relatively small range of keys. Another aspect that we looked into is scan throughput. Now here, this scan benchmark, again, a timeline throughput over time benchmark. This benchmark started immediately after the ingestion benchmark. And what we can see is that it took RocksDB almost 40 minutes to recover and optimize its data stores and reach a higher scan throughput, while EvenDB almost immediately reached a high scan throughput. So within this benchmark, EvenDB still wins. Now, RocksDB does run faster after it completes its storage optimization, but EvenDB does not try to optimize its storage in the background. And the scan through benchmark does not include many writes. So RocksDB has a lot of has the resources to optimize the storage without being affected by background updates. So in summary, EvenDB introduces a novel key value storage architecture that's optimized for spatially local workloads. It offers slow write amplification, a single level of storage without overlapping, and the memory serves both reads and writes. EvenDB outperforms RocksDB when the workload is spatially local, or most of the working set fits in RAM, namely an amount. And otherwise, both databases are in par. And we've demonstrated EvenDB's benefits on real both workloads and synthetic YCSB benchmarks. And with that, I'd be happy to answer any questions.
Thank you very much for the great talk, Aaron. Let's see if we have some questions on the Slack channel. I don't think we have questions there. So while we're still waiting for questions there, I have a couple of questions that I can ask. So I think in one of the slides you mentioned that RocksDB had like 4x slower ingestion rate compared to EvenDB. I was wondering like why that is the case and what is the exact workload that you ran? Is it like a sequential insertion of keys? Is it random insertion of keys? Can you provide more details of why RocksDB is so slow?
So the workload that we ran was the ingestion workload that reproduces the arrival of events from our production system. So those events are ordered by timeline, namely the actual order in which they arrived into the system, but they are indexed by the application name. So they have composite keys that are built by the application name and the timestamp. So what happens is that the insertion is distributed over the key range with hot areas because some keys are hotter, but it's not like tight sequential insertions like a serial insertion where all the keys are adjacent. So I think what happened there is that we basically covered a fairly wide range of keys in RocksDB. When it had to do the compactions, then it had to merge files that covered a wide range of keys. And so compactions basically affected most or a significant portion of each level. And this caused RocksDB to do a lot of heavy compactions. Even though the amount of data wasn't huge, it affected a large range, and so the write amplification was significant. And in our case, EvenDB isn't really bothered by that because most of those local insertions take place in chunks that have mounts. So the compaction basically takes place in memory for the most part.
I see. So I think I have probably one other question that I can ask. This is probably a slightly high level question, I think. So B plus trees already give you the spatial locality in that they don't do out of place updates. So like keys that are adjacent in the key space are going to be located sequentially on disk or whatever storage. So I was wondering, so is your requirement that you also need the high ingestion rates provided by LSMs while having the spatial locality? Is that why you want to optimize LSMs, not go with B trees or B plus trees?
So B trees in general, I think the main issue there is that insertions require, when you insert a single key, then you have to basically update a complete B tree node. and that's basically a random I/O. So it might have worked better if insertions were spatially local. We didn't really try, a B-tree baseline. So I'm not sure how that would affect, how this kind of workload would have affected an actual B-tree implementation. But in general, we saw that B-trees, the insertions are, they generate more write amplification than LSMs that buffer inserts and do batch compactions. So are more efficient in writes.
Mm-hmm. Yeah, and I also see good reasons why to optimize LSMs, which are already commonly used at many places to have this new property of supporting spatial locality lookups. Yeah, thank you for the great talk. I think, let me see one last time if I have any questions. Yeah, so feel free to ask any questions that you have on the Slack channel for Iran. He'll be happy to answer there. With that, I think we can go to the next talk. The next talk is Mad HTLC, because HTLC is crazy cheap to attack. The title intrigues me very much. I think Ita is going to tell about this paper. Can we have the video played, please?
Hello everyone, my name is Itai Tzabali, and I'll present a work titled Mad HTLC because HTLC is crazy cheap to attack. HTLCs are smart contracts used in many cryptocurrency systems, like the Lightning Network. However, they are known to be vulnerable to minor bribery attacks on Ethereum. In this work, we show these attacks are simpler, cheaper, and apply even to Bitcoin. We also propose a solution, Mad HTLC, which is practical, secure, and incentive compatible. This is a joint work with Matan Yechieli, Alex Manuskin, and Itai Eyal, and you can find the full paper in the Proceedings of IEEE Security and Privacy 21. I'll start with some background. So, cryptocurrency systems facilitate transactions of internally minted tokens among their users. They use the blockchain as the main data structure. These systems are operated by miners. They include transactions in blocks and in return receive transaction fees. They are incentivized to optimize their transaction choices. We refer to these optimizations as miner extractable value. The system tokens are associated with contracts. These are predicates evaluated on transaction data. A value transaction must satisfy the contract's predicate. We say a transaction redeems an input contract once it's confirmed, and each contract can be redeemed only once. Hashtime block contracts, HTLCs, are contracts established by two users, Ant-Man and Batman. They include the cryptographic hash function's output and the time OT measured in blocks. HTLCs are the basic building block for many cryptocurrency constructions, like off-chain payment channels, atomic swaps, contingent payments, and so on. The HTLC predicate states that Ant-Man can get the tokens by revealing a matching preimage, or that Batman can get the tokens after the timeout elapses. We refer to these as a hash lock and a time lock, respectively. Consider an HTLC instance initiated on block X. Batman can get its tokens starting only at block X plus T, and only if they hadn't been taken yet. We call the miners are those who pick which transaction is included and in which block. The cryptocurrency constructions that use HTLCs make the following assumption. If Ant-Man publishes a redeeming transaction before the timeout, then that transaction is indeed included in the blockchain. There is a known issue here. This assumption neglects miners' incentives, specifically their MEV optimizations. This misalignment opens a bribery attack opportunity for Batman. Instead of doing nothing, he can bribe the miners to exclude Ant-Man's transaction until the timeout elapses, and then to include his transaction instead. Intuitively, consider an HTLC contract holding 5 tokens, and Ant-Man's transaction offering a single token as a fee. According to the assumption, the miners include Ant-Man's transaction, so Ant-Man gets 4 tokens, Batman gets none, and the miners get 1. However, if Batman decides to offer a higher payout, say 2 tokens, then the miners are incentivized to take his transaction instead, resulting with 2 tokens for them, 3 for Batman, and none for Ant-Man. This is clearly better for Batman and for the miners. Windsor et al. Suggested coordinating a bribery attack using elaborate smart contracts. Their suggestion applies only to Ethereum, but not to Bitcoin. It also requires prior deployment, meaning the attack has costs regardless of its success. They analyzed the required bribe to incentivize a single miner to support the attack, and show that if all other miners also support the attack, then that cost is independent in timeout T. However, if some miners do not support the attack, then the required cost is exponential in the timeout. This suggests that longer timeouts can mitigate these attacks by making them too expensive to execute. In this work, we present a simpler attack variation. We also tighten the result regarding the attack cost, showing it is independent in the timeout if all miners are rational. Our variation does not require a coordination smart contract, but simply uses the transaction fee mechanism. This makes it Bitcoin compatible and means it requires no prior deployment. Therefore, it has no cost if the attack fails. For the analysis, we consider a game played by all involved parties, Ant-Man, Batman, and the miners. We consider rounds or subgames describing the creation of the T blocks. The suitable solution concept for this game is subgame perfect equilibrium. This captures the ongoing decision-making that all involved parties make throughout the game progress. As an example for SP analysis, consider a game of tic-tac-toe. To decide the best action in each turn, the player simulates all possible game extensions, considers the possible outcomes, and chooses the action that leads to the desired result. Subgame perfect equilibrium is when each player is satisfied with their action in each step. This analysis technique is called backward induction. The game results are recursively propagated back to the decision point. Our analysis shows that the required bribe is independent in T. This means that increasing the timeout does not make the attack more expensive. We also found multiple instances on the Bitcoin network where the attack is extremely cheap and highly profitable. For example, we found several HCLCs holding over $26,000, where the required attack costs are only 2. I should mention that although the simplicity and high profitability, we are not aware of this attack taking place on Bitcoin as of today. This is probably due to the current MEV optimizations are still immature. So, even though today's miners do not optimize for this, that's hardly something to rely on. And the obvious question is whether we can prevent this attack. For example, what if Ant-Man counter bribes? Well, in this case, Batman can counter bribe, and so forth, resulting in a bidding war. Our analysis shows there is an asymmetry here, and that Ant-Man can win this bidding war with a fee linear and a secured amount, about 1% for realistic parameters. This is very expensive. Going back to the previous example, Ant-Man would have needed $260 fee, which is 10,000 times more than what you originally offered. So counter bribes are not practical. We need a systematic solution to this problem. We present MAD HCLC. Recall the problem is that HCLCs don't consider miner incentives. So let's not do that anymore, but actually use the miners to enforce the desired execution and to deter attacks. Here is a quick overview for the remainder of this talk. First, I'll detail the MAD HCLC contract and the security and the incentive compatibility proofs. Then I'll discuss our Bitcoin and Ethereum implementations and what happened when we deployed them on the main networks. Finally, I'll present our Bitcoin MEV infrastructure. The design principle of MAD HCLC is mutual assured destruction. This is a notion from game theory, describing a setting where two parties refrain from attacking each other, as doing so will result with both of them losing. This is a deterrence mechanism, and in MAD HCLC, if either Ant-Man or Batman misbehaves, then they both lose. The contract itself comprises 2 subcontracts: the deposit, which carries the main HCLC functionality, and the collateral, which is optional and only used to prevent spitefulness. The separation is only for Bitcoin compatibility, but the subcontracts can be consolidated on Ethereum. The contracts use a time lock and 2 hash locks, denoted by a hash lock 1 and hash lock 2. The time lock is just like the HCLC time lock, and a hash lock 1 is just like the original hash lock in HCLC. Hash lock 2, however, is an addition from MAD HCLC. The deposit predicate has 3 redeem options. Either Ant-Man gets the tokens by solving hash lock 1. This is just like in the original HCLC. Or Batman can get the token by waiting for the timeout to elapse, like in the original HCLC, but now you also must provide preimage for the second hash lock. Alternatively, anyone can get the tokens by providing the 2 preimages for both hash locks. When I say anyone, I actually mean any miner. If a miner sees a transaction that reveals both pre-images, she can just create a transaction of her own and take the tokens herself. This is actually an MEV opportunity. The collateral predicate uses the same lock parameters, but it is a bit different. Either Batman gets the tokens after the timeout, or any miner can get the tokens after the timeout by presenting the two pre-images. So, is this secure? Why does it work? Our first step is to list the desired possible interactions that Ant-Man, Batman, and the miners can have with a mad HTLC instance. These include the creation, the initiation, and the redeeming of an instance. For example, we consider that redeeming using a hash log requires the redeeming party to have the matching pre-image beforehand, or that miners initially do not have the pre-images and can only learn them if they are published by a different party. Now we prove these are indeed the only possible interactions. So we define an ideal functionality F, detailing the desired possible interactions in an ideal world. We also define a protocol pi that states how mad HTLC instance is created, initiated, and redeemed. This protocol uses the hash function in the blockchain, which we model as global ideal functionalities. So we consider the protocol pi in a hybrid world. The last step is showing the hybrid world with protocol pi and the ideal world with functionality F are indistinguishable. The possible interactions with the contract give rise to a game, played by Ant-Man, Batman, and the miners. We use subgame perfect equilibrium analysis and show mad HTLC is incentive compatible. No party gains by deviating. I'll give some intuition. Consider that only one preimage is published. Then the miners do not know the other preimage and can get their tokens. This scenario matches the intended behavior. However, if both preimages are published, miners will simply take the tokens themselves. This scenario describes either Ant-Man or Batman attacking. Also, note that if Ant-Man publishes his preimage, then Batman is unable to get the deposit tokens. So a spiteful Batman might just publish the second preimage anyway. This is where the optional collateral contract comes into play. If Batman does so, he will lose the collateral tokens, and if not, he will get to keep them. I'll now present some implementations and main network experiments. We implemented mad HTLC using Scrypt for Bitcoin and Solidity for Ethereum. Mad HTLC is slightly more complex than the original HTLC, so the interaction transactions are slightly more expensive. In Bitcoin, the additional costs are about a few dollars. For Ethereum, the basic implementation is a $150 overhead, but this can be reduced to about $10 for an amortized version. Please note the overhead is independent of the secured amount, which can be thousands of dollars. Taking as an example the $26,000 for Bitcoin contract, $5 are way cheaper than the $260 required for the HTLC counterbribe. I'll also mention that for the off-chain payment channels, the HTLC or the mad HTLC is only used when unilaterally closing a channel. This is not the general case and happens only if one of the parties is trying to cheat or becomes irresponsive. So even this lower overhead is incurred only if there is a dispute. We deployed mad HTLC on Bitcoin and Ethereum main networks. On Ethereum, some of our transactions were Fortran, showcasing MEV in action. This is expected as MEV on Ethereum is widespread. On Bitcoin, however, all our transactions were confirmed. We didn't observe any related MEV optimizations. So why don't we see MEV on Bitcoin yet? Is it because it's too hard? We show this is not the case by patching the popular Bitcoin Core client. Our first patch is to support the HTLC bribe attack, requiring only 150 lines of code. The code identifies Batman's bribe, delays Ant-Man transaction, and includes Batman's transaction after the timeout elapses. We also created a general MEV infrastructure. Using RPCs, it exports data to an outer Python module, where one can implement any MEV logic features. For example, we implement the mad HTLC enforcement logic, a miner looking for a published preimage and creating a transaction of their own. This patch required 350 lines of code. To conclude, HTLCs are vulnerable on Bitcoin as well. The required bribes are cheap and the potential reward is high. The attack relies on MEV, which is easily implementable, and simply increasing the timeout does not help. We introduced mad HTLC, a simple plugin replacement with a minor overhead compared to the secured amounts. It is secure and incentive compatible, it's easily supported by miners, and its code is available online. Thank you.
Thanks for the great talk, Itai. Let's see if we have questions on the Slack channel. Let's wait for more questions on the Slack channel. Maybe in the meanwhile, I have a couple of questions that we can probably try to answer. So So from what you said, it looks like the current blockchains are at a significant risk of HTLC attacks, especially given that it's very cheap to mount these attacks. So I was wondering if HTLC was actually a bad contract design to begin with. Are there other secure alternatives to HTLC that achieve the same functionality that HTLC provides? Or in other words, if you were to design the same functionality that HTLC offers, would you design a different primitive or a different way of doing things?
Yeah, that's a good question. So first of all, my student Itai Tsabari was not able to attend, so I'm Itai Yal, and I'm covering for him. I didn't massively change between the recording and now. As for your question, HTLC turned out to be a very useful primitive. It's used in a plethora of smart contracts. Payment networks are the most common and the most famous, but really, in any situation where two parties interact off the blockchain and then should settle on the blockchain at a later stage, we need really something similar to HTLC, because we need an operation to happen on the blockchain. This should be allowed because either party should be able to unilaterally settle the situation. But this ability of the party should allow the other party to refute this settlement in case the first party is cheating. And so this sort of interval is really a core technique for smart contract design. And the fact that the first transaction happens on the blockchain and there is some interval until the refutation happens, this allows an attacker to issue a bribe attack. There are no concrete alternatives I'm aware of outside MAD HTLC.
I see. Thank you. I think meanwhile I have another question. So you also talked about did you also upstream your fixes to Bitcoin Core? Can you also elaborate a bit about that experience?
Mm-hmm. So the Bitcoin Core updates, we did two of those. First of all, we were curious why people were not using it, so we tried to figure out whether it was hard to take advantage of bribes against HTLC. And it turned out to be very easy. So the reason these bribe acceptance is not implemented is simply because it is, so far at least, not common, and miners simply didn't bother to implement it. Really took 150 lines of code, like I said in the recording, so this was trivial. What was more important for us was to implement the general MEV infrastructure that would allow miners to take advantage of MAD HTLC implementation, and then protect users that use MAD HTLC. This required getting a bit more involved, and it was important for us to make this accessible. So the actual programming of the logic is done in Python, and the Python drives the Bitcoin client to manage the contracts.
I see. Thank you. If you have more questions, please post them on the Slack channel. I think the authors will be more than happy to answer it there. Thank you so much for the talk. With that, I think we can go to the next talk.
Thanks very much, Sean.
Yeah, thanks. The next talk is from Alex Technian from Technian. He's going to tell us about characterizing, exploiting, and detecting DMA code injection vulnerabilities in the presence of an IOMMU. So can we have the video played, please?
Hi, my name is Alex, and I'll present our paper, Characterizing, Exploiting, and Detecting DMA Code Injection Attacks in the Presence of an IOMMU. First, let's start with DMA. DMA, or Direct Memory Access, is a common hardware feature that allows an attached device to access the main memory without involving the CPU. That's devices like GPUs, SSDs, network cards, USB dongles, and many others. DMA also allows a malicious device to read or modify memory that it was not supposed to. This is called a DMA attack. It's a side channel attack where a malicious DMA capable device compromises the system. One notorious example is this thin FireWire unit, which is basically a Lenovo ThinkPad with a FireWire adapter and can be used to take over a target machine. You just approach the target machine, plug in the dongle, and gain control. Easy enough. To prevent arbitrary access to the memory, a modern systems have IMU hardware. The IMU works for devices just like the MMU works for processes. It provides virtual memory support for the attached device, meaning that the device can access only pages that are listed in the IO page table, and the page table is controlled by the operating system. So within an IOMMU, the device can access the main memory only via IO virtual addresses, IOVAs. And this prevents the device from accessing any memory pages that were not explicitly set up by the operating system. And this way, the IMU is supposed to prevent DMA attacks. First, let's see an example of how IMU is used in the DMA API in Linux, and then I'll explain briefly why IMU is insufficient to provide security. This is an example of a sent packet. First, the device driver maps the buffer. That's the virtual address of the buffer in red. It allocates an IOVA. It updates the DMA map operation, updates the page table. That's the blue box on the side. And now we have a mapping. Now the red virtual address and the yellow IO virtual address point to the same physical page. Next, what happens? The device reads the buffer using the IOVA, which populates the IOTLB. The IOTLB is has the same function as the TLB for MMU. It provides fast lookups for translations. Now, when the operation is complete, the device driver unmaps the IOVA. It removes the entry from the page table, and it flushes the IOTLB. So without flushing the IOTLB, the device can still gain access to the physical page because of the fast lookup. We flush the IOTLB and thus prevent the device from accessing this physical page, and we free the IOVA. Now, a problem is the problem, and the problem is something that's called a sub-page vulnerability. In the case of IO, many packets are much smaller than a whole page. It can be like an ARP packet, an ICMP, DHCP, any control packet. And in this case, a small chunk of the page is actually used. But when mapping it, the whole 4K is exposed to the device. And unsurprisingly, there were a couple of projects recently. One of them is the Thundercloud project, and it was showcased in NDSS in 2019. They chose an FPGA that can masquerade as an Intel NIC, and among other things, and gain access and act as a malicious device and compromise the system. Another was a work by Kupfer in his master's thesis, where he was able to take advantage of a DMA vulnerability bug in the FireWire device driver and actually execute a code injection attacks on the target machine. So the problem with these two jobs, what is missing is that there's no structured way. We don't know how to find new DMA vulnerabilities. We don't know how to assess a DMA vulnerability. Is it something that is very dangerous or not? And the most troubling one is we know that there are vulnerabilities, but how many are there currently in the operating system that we use? How leaky is the ship? And I'm here to try and answer some of these questions. So first, we'll talk about characterizing the sub-page vulnerabilities and the code injection and attack attributes. And then we will talk about the rest of the contribution. So sub-page vulnerability has 4 types as we see it. One is when a device driver, for some reason, maps its own metadata because it collocates the I/O buffer and its metadata on the same page. But more often, what happens is it's by OS design. And examples are FreeBSD and Windows, where the and macOS, where the I/O metadata sits just in front of the I/O itself. So there is no way actually to map the I/O without also mapping the metadata. The third type is when you have two IOVs mapping the same physical page. One problem with this kind of vulnerability is when you unmap one IOV, the device can still access the same physical page because it can use the second IOV, which renders the unmap operation essentially useless from a security standpoint. And lastly, we have the incidental exposure. This happens usually randomly. The first three are easily detectable, detectable with a static analysis. The last one has a random nature. What happens is an I/O buffer is allocated, and another buffer of similar size is allocated from the same page. So when the I/O buffer is mapped, all of the other buffers that reside on this physical page are also exposed. And we see how it can become a problem in the next slides. So let's see an example of something live. One example is NVMe fiber channel driver. And in the init request, when the host wants to read something or write something for a storage device via the fiber channel, the communication happens via DMA. And in this case, what happens is this command data structure, it's 96 bytes long, is mapped to the device. The second thing that happens is the response is also mapped, and its size is 32 bytes, sorry. And it allows the device to write to that page. So innocuous enough, but when we look into the data structure, we see that the command and the response both reside one next to the other, and essentially allowing the device both read and write access to the same page at the same time. And it also exposes all the other fields in this FCP operation data structure. One of those being FCP request, which contains none other than this callback pointer, which when overwritten will allow the device to effectively gain control of the machine, for example. Which leads us to the attributes needed for successful code injection attack. So you need three things. You need the virtual address of the malicious buffer. So how do you override this callback? And with the both read and write access to this page, we can learn the page address, the CPU address of this page, because it's one of the fields. One of the fields points to the head of the data structure set. The other thing we define is the callback function to override. And the third thing, we need an opportunity, namely that once the callback function was overwritten, it will not be reset and instead be executed by the CPU. And that's exactly what will happen in the case of the NVMe fiber channel operation. Next, now we see how dangerous subpage vulnerabilities are. Let's talk about detecting them. So we provide static analysis for the first three types, dynamic analysis for runtime analysis of your system, and we provide a kernel 5.0 analysis showing what kind of numbers or how many vulnerabilities are there today in kernel 5.0. We call our static analysis SPADE, and it works recursively. It starts from a DMA map operation, and that's an example. We see that pointer is mapped, and we look up and we see that it's a void pointer, which is kind of useless. But let's see where's FC DMA map signal function is called, and we see that we find it one example in NVMe init request. We find that the pointer actually is an op pointer, and if we scroll up the screen, we find the name of the data structure, and we analyze this data structure with tools like PA-hole. We find callbacks inside of it, and thus we find the vulnerabilities that we were looking for. Second, we have DKSAN. It's a runtime analysis used on a kernel address sanitizer, and you can read more about it in our work. And she provides these 4 types of vulnerabilities where a buffer is mapped randomly, in essence. And you find multiple examples of non-IO buffers being exposed. Both tools are open source. You can find them on GitHub. And finally, we provide a new compound attack. So the example is Linux kernel, where an IO buffer has SKB shared info, and it happens for specifically for all network buffers, and it contains a callback function. The problem is that it's not enough. We have no opportunity because the structure is overwritten after the DMA map, and the problem is we don't have the CPU address. And because we have no more time, I can't go into details of a DMA attack, of a compound DMA attacks. So I urge you to read our paper. Thank you.
Thanks for the great talk, Alex. Let's see if we have questions posted on the Slack channel. We don't have any so far, so maybe I can ask you a couple of questions. So you talked about different subpage vulnerabilities, and then you mentioned that the OS metadata co-located with the IO buffers is a problem in BSD, Windows, and even Mac. Is Linux immune to this problem, this vulnerability? And if so, did the developers anticipate this particular subpage vulnerability in that they did not place the kernel data structures in the same page, and they were careful about that, or is it just by chance?
Well, the example I've shown shows that they didn't in NVMe devices. So the specific problem I was mentioning is for networking. So networking metadata is in all the systems is linear, in the sense that the metadata and data are always on the same page. In Linux, it's just a matter of flexibility. You have the data, and then the metadata is on a separate page. But again, the final example that I just started showing in the talk of the compound attack is when we need to have more intelligence in our attack, namely locating the time of attack, when you can modify the call pointers, when to find them, obviously, and we find them in the metadata that is called SKB shared info at the end of the data page. So what happens in Linux? So you have the SKB, which is the metadata for a network IO packet. Then you have the data itself, and at the end of each IO packet, small and big, you'll have SKB shared info, which holds additional metadata and a callback pointer as well. So the short answer is no. There is no operating system today that does not expose a sensitive metadata in its IO path.
Mm-hmm.
So,
okay. So let's see. So the other question that I had was, you talked mostly about the code injection vulnerabilities. Are there also other problems like silent data corruption or something like that the devices can cause to the system, which may cause the system crash or something like that?
Yes. So with just trivial attacks that data corruption is something that you can't avoid with software, because the data is written by the device. You don't know how it's supposed to look, right? So data corruption is something that we can't prevent. We can prevent access to things like the control path. You don't want to allow an attacker to execute malicious code with root credentials. kernel panics, obviously, if you corrupt those callback pointers, just if you put a null in there, you'll get a kernel panic, and you don't need any compounder network. The callback pointer is there, and null is null. So yeah, there are different attacks. Just code injection is the most severe in my mind. So where you just can run any random code on the machine and just gain control. In theory, you can also silently try and steal data, like in the case of the metadata shared info. You have addresses for other pages for when the packet is made of different pages, different buffers. So in theory, you can probably change the response pointers before they are mapped, and thus make the OS map its own memory and send it to the attacker, for example. But it's a theoretical example where we don't actually change the code execution, but we can make something pretty malicious and scary to happen.
All right. Thank you. Very cool work.
Thank you.
Let me see if they have any other questions. So please feel free to post your questions about this paper on the Slack channel. I think Alex can answer them offline. So I think with that, we can move to the next paper. We have the fourth paper, which is PINT, probabilistic in-band network telemetry. This was presented at SIGCOMM. Rand Ben is going to tell us about this paper. Can we have the video played, please?
Hi everyone, my name is Rand Ben Basat, and today I'll be talking about PINT, or probabilistic in-band network telemetry. And this is a joint work with people from Harvard and Queen Mary University of London. And PINT has really been enabled by this trend of programmable networking devices that we have now. And since we have these networking devices, we started writing papers about them, saying, look, now we can do some cool stuff. But actually, this is now becoming a reality. So we see more and more companies that are actually placing these programmable devices in production networks. And one of the killer applications for these switches is telemetry, right? And telemetry is about knowing what's going on in the network. So I want to know everything that's going on with my packets. So for example, I may want to know, is there a congestion or a queue buildup somewhere in the network? I may want to know, do the paths taken by the packets conform with my policy? Like maybe I want them all to go through a firewall, right? And another type of question is, can we increase the rate at which some connection in the network send traffic without creating a queue buildup somewhere, right? So to that end and others, the INT protocol was proposed. And INT stands for in-band network telemetry. And the idea of INT is conceptually simple, right? So the designers of INT thought, okay, so we want to collect some information like a switch ID, let's just add it to packets, right? So let me show you what it looks like. So we have this path, and the first hop on the path, it's called the INT source. It adds to the packet something that's called the INT header. And the idea here is that this header would tell the other hops on the path what information we're trying to collect, like maybe the switch ID, right? So it also adds its own switch ID and sends it to the next hop. The next hop reads the INT header, figures, okay, we're collecting, switch IDs. Let me add my own and send it. This way, the packet goes all the way to the last hop, which removes this information from the packet. So this protocol is transparent to the sender and receiver. And now that we have this information, we can figure out, in this example, the path. Right? So let me give you a few use cases for telemetry. The first is congestion control. So just like on the road, if there's too much traffic on a single route, then there's going to be congestion and there's going to be delays. Right? So congestion control is about fine-tuning the sending rate of the different connections in the network, so that overall we won't cause congestion at no link in the network, right? And it turns out that a state-of-the-art solution for congestion control, it's called HPCC, and it's running in production in Alibaba, is using INT to collect queuing information from the network, and it uses that to fine-tune the sending rate. Right? A second use case is path discovery, and it is that there could be many different passes leading to the same destination, and I want to know things like which path did my packets take, or what routing rules do they follow, or more general, do all passes conform with my policy, and things like that. A third use case is for network debugging, right? So I want to identify switches or links that have high latency. And for example, there can be an imbalance where one path is really loaded while the other one is underutilized, and we want to shift some traffic. And this can also be done using telemetry. Right? So INT is really general, right? Like you can basically collect everything that's available to the switch. You can collect latency information, you can collect queue information. It's already running in production in major companies, but it's also pretty expensive. And the reason is that this information bits that we add in each hop adds up, and it becomes a problem. And if you think of collecting even just like one information type, like the switch ID, if you want to know the path, then every switch would add 4 bytes of information to the packet, and this overhead increases multilinearly in both the number of information types and the length of the path, like the number of hops. So let me tell you why this is an example. So in life before INT, right, you could take the maximal transmission unit, like the largest size a packet is allowed to have. And other than a few bytes that is used for the header that we use for the routing, everything else would be the payload or data of the packet. Now, what happens when you enable INT is that you have to provision enough space on the packet so that the switches can add in their information without exceeding this maximum size. And this means that we have now fewer bits for the payload, for the data. So if I want to send the same amount of information, I will need to send more packets. Right? And we did an experiment in which we add this overhead to packets, right? So the x-axis here corresponds to adding 1, 2, 3, 4, or 5 information types on standard fat tree topology. And the y-axis is some metric of how well the network is performing. It's called normalized goodwood. And what we saw is that even if you add just like one information type, like the switch ID for path tracing, it already costs quite a bit. And if you want to run HPCC, this congestion control algorithm I talked about, you actually need 3 different types of information to tune the sending rate. And this would cost you even more. And if you want to run HPCC while collecting the path information, it will set you back even further. So it really adds up, right? Second issue with this added information is the switch processing time. And the idea is that the switches have a fixed bit rate in which they can serialize and deserialize information. So if we have now packets that are larger because of the INT information, they would spend more time at the switch. And from our calculation, every information type that you add to the packet would cost you about 1% increase in switch latency. Another problem is the collection cost. And what I mean by that, if you think of a network, we have many switches, we have a lot of packets going through them, they all generate information. And then we need to move this information to a centralized location. It's called the collector. And the problem here is that it really is a lot of information, right? And in practice today, people are running INT only on part of the data in the network, only a part of the traffic. And this is just because the collection cost is that high. Okay, so to that end, we designed PINT. PINT is probabilistic INT, probabilistic in-band network telemetry, and the goal is to minimize the number of bits we add to packets. And our insight in PINT, like the reason why we believe we should do that, is that a lot of the applications that are using telemetry don't actually need all of this information that INT generates. They need some aggregate form of this information. And if we can do this segregation in the network at the switches, we won't need to send all this information to the collector. Right? And our code is open source if it's interesting to anyone. But let me try to first explain why we believe a probabilistic approach is the right way to go. And in very roughly, this probabilistic techniques I'm going to talk about trade the number of bits you add to each packet at the, like they reduce it at the cost of approximation. And you can think of approximation like something in this figure, but there are different types of approximation we use in Python. One is we do some numerical approximation of like the latency measurements, right? And the idea is that it's often not really important to know what are the exact latency numbers. What is interesting is to know when the latency is too high or when there was a significant change in latency, and we can capture that. Another type of approximation is that we may require multiple packets to read the information out of the network. So if you think of discovering the path, then INT would add all the switch IDs on each packet, and now you know the path from a single packet. But if we want to reduce the overhead, we can spread this information across multiple packets, so it would be a while before you know the right path. But it's also fine because usually flows like connections in the network have multiple packets, and even if you assume that they have only a small number of packets, it's already enough to reduce the overhead by quite a bit. What are our techniques here? So we use global hash functions, and we use them everywhere, including the algorithms. So for example, if we run multiple queries concurrently, like maybe congestion control and path discovery, we want the switches to implicitly agree what type of query they should run on the current packet. Right? Another technique is we approximate real valued numbers like latencies to reduce the number of bits we need. And also we use coding to spread information across multiple packets. And all of the use cases I mentioned, they all use some subset of these techniques. So let's go back to the congestion control example, right? So I told you that HPCC, this algorithm, is using INT, right? And the idea is that it captures several information types from each hop. And then the signal that it uses, so for every hop, it collects 3 different metrics. It combines them somehow using this function f, and it checks what's the maximal value, like which switch is the most congested, right? What we do in Python is we move the computation of this function f to the switches. Well, we cannot exactly do that because the switches are constrained. We can do some approximation of this function at the switches, and now we can track just the maximal f value along the path, so we don't need to collect all of the queuing information, and this saves a lot of bits, and we can further approximate it to reduce the number of bits and so on. And also in Python, we do probabilistic rounding so that we would get the right signal in expectation, and now the sender, after receiving a few of these feedbacks, can look at the average and find out just the right sending rate. Okay, let's go to path tracing, right? So INT does that from a single packet. It just carries all the switch IDs. But in Python, for example, one thing we can do is we can look at the subset of the switches on the path and just put these on the path, right? But actually, we can do even better than that. We can use coding to mix up the subset of switches together on a single packet. And this reduces the number of packets we need to read out the path. And we can even do this with a single bit, which sounds weird, but again, like it's only a matter of how many packets we need before we can read out the path. So we can do this even if we add just 1 information bit on each packet. And what we saw is that even with a single bit of information, Python already improves over the state of the art. So let me give you some motivation for why we use coding, right? And this is going to be like a toy example where we only have 2 switches on the path A and B. And if we think of a baseline that just samples one switch ID, right, to reduce the overhead, then it will get some switch ID on the first packet, like maybe A. But now, on average, it would require 2 packets before it can get the other switch ID, which is B in this example, right? So on average, it would require 3 packets to read out this path. Now, think of an alternative algorithm that uses coding, and instead of always sampling one switch ID, with probability 1/2, it's going to sample one switch ID, and with probability 1/2, it's going to write a bitwise XOR of A and B. Now, what happens is that if the first packet carries some identifier like A, right, then the number of packets we need before we can figure out that the second identifier was B reduces significantly. And the reason for that is either we get B and we're done, or, which something that also happens, probability 50%, we would get the bitwise XOR of A and B. And in this case, we're also done because B equals the XOR of A and A XOR B, right? So on average, we would need only 4/3 of additional packets to figure out the second hop, and this reduces the number of packets overall. So Pint solves the overhead issues. We now, by reducing the number of bits we add, we reduce the good to degradation if we want to collect telemetry, and we also reduce the switch processing time. And with that, I will conclude, and I'll be happy to take any questions. Thank you.
Thank you for the great talk, Ran. I actually forgot to introduce Ran before the talk. Ran is actually an assistant professor in the CS department of UCL. He was a postdoc at Harvard before that and received his PhD from Technion. Ran is here to answer our questions. Let us check if there are questions on the Slack channel. While we wait for more questions in the Slack channel, I think I'll go ahead and ask some questions. Ran, great talk. I was curious about your path tracing example that you presented, right? So if I understand it correctly, in Pint, with the path tracing use case, you need to look at multiple packets to say which path the packets actually took. So I was wondering, if there is a problem in the flow where the flow is like just short-lived, it just was able to send only a few packets, after which it hit a failure or something like that, would the original in-band network telemetry will be able to give you the exact information of the path, whereas Pint will not be able to because you don't have enough packets? Is that a problem? Is that a problem in practice?
So you got it right. So in Pint, you cannot, if you use coding, you cannot read anything from a single packet. And then if you have flows that are short-lived, then you need to understand what's the minimal number of packets you are willing to assume that a flow that you care about has before you can read out the path. And this is all about, like, if you assume that a flow has at least 5 packets, we can use that. If you assume it has at least 2 packets, we can use that. If you don't assume anything, we cannot really reduce the overhead at all.
Mm-hmm. So more generally, right? So one of the questions I was wondering is, are there class of applications where probabilistic nature of Pint would not be very helpful, that you need the exact information to be reproduced? Let's say you're doing some forensics or something like that, where you cannot live with probabilistic data. Have you seen some applications? I don't know about those applications.
So I think, like, in some cases, you may want to ensure that all packets conform with some policy, right? Like you don't want a single packet to get to a destination without going through a firewall or something. And in this case, you cannot run Pint, like you shouldn't. But I think for most cases, it's not a requirement that you have to make sure that every packet follows it, and then you can benefit.
Yeah, makes sense. Yeah, and the final question that I had was about the overheads, the compute overheads that the Pint approach has on the switches. Does that prevent any sort of, like, how much is it, and does that prevent, like, implementing other things on the switch, or does it interfere with existing functionality in the switch?
So I think all of our algorithms either use none or a very minimal amount of state, like use very little switch memory. What they do use though is like they require some operations. This is why we need to run it on a programmable switch. And depending on how good the performance you want the algorithm to make, the more resources they would need, like the more computations per packet they would need. But I think in most cases, they would require at most like 10% of the number of operations per packet it can do.
Yeah, thanks. I think we have one other question from the attendees. I don't know who that is. Can you please unmute and ask?
Yeah, it's me.
Yeah, go ahead.
It's probably me, if there's just one. I have a question. Techniques that use sort of piggybacking on communication to measure things generally suffer from the fact that the amount of information depends on the amount of traffic that happens to be there. This was encountered for rate control by Mellanox in RDMA years ago. And the question is whether your technique aggravates the situation or is kind of orthogonal to that.
So I think like in general, there are two ways that people are running INT. One is they piggyback the information on packets like what I described here. And the other one is using what's called postcards, where the switches, if they detect that some information is interesting, they would directly send it to the collector without piggybacking it on the packet. And I think like the same algorithms we use in Pint, you can also fit them on the switches for the postcard mode, and then you wouldn't need to piggyback things on the packet itself.
Okay, thank you.
Do we have more questions? Let me quickly check. No, I don't think we have more questions in the Slack channel. Please free to post your questions there, and I think the others can answer offline. Thank you, Ranbin. Yeah, so with that, we have come to the final paper of this session, which is self-adjusting advertisement of cache indicators with bandwidth constraints. Itamar will tell about this paper. Can we have the video play, please?
Hello, my name is Itamar Cohen, and I'm a postdoc fellow at the Politecnico di Torino. I will present the paper, Self-Adjusting Advertisement of Cache Indicators with Bandwidth Constraints. This is a joint work with Gil Inziger and Gabriel Skalusub from Ben-Gurion University of the Negev. Network caching is a fundamental building block in multiple networking environments. Commonly, a user is equipped with one or more caches. If the user fails to retrieve the requested datum from a nearby cache, then he has to access a remote server, thus causing a high cost in terms of delay, energy, and bandwidth. To help the user deciding which cache to access, each cache periodically advertises an indicator, which is a compact data structure that represents the list of items currently stored in the cache. Using these indicators, the user can select a cache to fetch the requested datum from. Such indicators are widely used in multiple networking domains, such as content delivery networks, 5G networks, and information-centric networks. We now zoom into the indicators advertisement mechanism. Due to bandwidth constraints, the cache usually cannot advertise a full list of the items it stores. Instead, the cache advertises a compact representation, for instance, a Bloom filter. Such small indicators save a lot of bandwidth and space, but are inaccurate. That is, they exhibit false positive indications. The cache may use larger indicators that are more accurate. However, due to bandwidth constraints, the cache may advertise such a large indicator only once in a while. This results in an increased probability of false indications due to staleness. For instance, the user is now looking for item 888 that was evicted from the cache after the cache has transmitted the last advertisement. The item is not stored in the cache anymore, thus causing a false positive event, resulting in an unnecessary cache access. Furthermore, consider the case where the user is looking for item 666 that was inserted into the cache after the cache has transmitted the last advertisement. The user doesn't know that 666 is already stored in the cache and therefore accesses a remote server. This is a false negative event. Sometimes it is possible to save bandwidth by sending delta updates that only include the list of changes since the last update was sent. In our example, only the bit indexed 2 was changed since the last advertisement. Hence, sending a delta update is cheaper than sending a full update. However, when the number of changes since the last advertisement is large, sending such a delta update is not beneficial anymore. We assume that whenever this is cheaper, the cache advertises only delta updates. To understand the importance of the advertisement strategy, consider this graph. The graph illustrates the probability for a false negative event as a function of the update interval, namely the number of requests between subsequent updates. Note that both axes are logarithmic, and still the plot shows a steep increase. In particular, when the update interval is 1K, then the false negative probability is 10%. As we have just seen, every false negative event may result in an unnecessary access to a remote server at a cost that is typically at least 10 times the cost of a cache access. Paying a penalty of 10 in 10% of the requests may translate to doubling the expected cost of a data access. We now see a similar plot, but for the false positive probability. However, the false positive probability increases with the update interval at a much lower slope. Practical implementations of cache advertisements currently use some crude estimations and rules of thumb. For instance, the widely used Squid cache advertises its content once in an hour, and indeed, its spec relates to tuning the update interval and the indicator size as an open problem. I shall now overview our model. An access to a remote memory costs M, that is higher than the cost of an access to a cache. We normalize costs so that the cache access cost is 1. U denotes the update interval, measured by the number of requests between subsequent updates. I denotes the indicator size. We consider bandwidth constraint, where the average bandwidth used for advertisements is bounded to at most B bits per request. Hence, if the cache sends a full indicator of size I once in every U requests, we must have I over U at most the bandwidth budget B. Our goal is to find a configuration minimizing the expected total cost while satisfying the bandwidth constraint, where the total cost is the sum of the cache access cost and the memory access cost. And by configuration, we mean the tuple of an indicator size and an update interval. Let us overview our algorithmic concept. To get some insights about the problem, we consider two distinct traces, namely Scarab and Wiki. Of course, full details about the traces and the evaluation settings are in our paper. For each trace, the pink left bar shows the cost obtained by one configuration, and the black bar shows the cost obtained by another configuration. The figure shows that the pink configuration that does better for Scarab does worse for Wiki. We now vary the cache policy and observe the same phenomenon, namely a configuration that is superior for one concrete setting is inferior for another setting. Finally, varying the cache sizes unveils a similar phenomenon. We conclude that no single fixed static configuration does best in all distinct settings. Hence, we suggest using an adaptive algorithm that self-adjusts the configuration once in some t seconds. We now turn to detail our algorithm, CAB, standing for Cache Indicators Advertisement with Bandwidth Constraints. Our algorithm is composed of two modes of operation, namely full indicators and delta updates. While the full indicator mode, intuitively, we try to reduce the penalties of misindications by equalizing the penalty incurred by false positives and false negatives. Typically, the cost of a false negative is larger than that of a false positive. This is because a false positive typically results in an unnecessary cache access at a cost of 1. However, a false negative typically results in an unnecessary memory access at a cost of m, while the user could have retrieved the datum from the cache at a cost of 1. To equalize the penalties of false positives and false negatives, we therefore would like to have a single false negative event for every m-1 false positive events. To do so, we tune our configuration as follows. We recall that the main source for false positives is inaccuracies in the indicator itself, and therefore, when there are too many false positives, we enlarge the indicator. On the other hand, when there are too many false negatives, we decrease the update interval, thus decreasing the staleness, which is the source of false negative events. We'll now overview CAB's delta updates mode. Intuitively, advertising either one change in the indicator once in a second or 10 changes once in 10 seconds require the same bandwidth. However, advertising one change every second reduces staleness, thus reducing the false negative probability. Hence, once at the delta updates mode, we use the minimal possible update interval and focus solely in adjusting the indicator size to comply with the bandwidth constraint. However, when the cache's content rapidly changes, it may become impossible to satisfy the bandwidth constraint using delta updates, even if we shrink the indicator to its minimal feasible size. Once this phenomenon happens, we increase the update interval to b over the size of the minimal feasible indicator, I min. Thus, we verify that we satisfy the bandwidth constraint by sending I-min bits once in every update interval. This implies also returning back into the full indicator regime whenever the bandwidth constraint dictates. We conducted an extensive evaluation study using 8 real-world traces, 3 cache sizes, and 4 state-of-the-art cache policies. This experiment evaluates the performance of CAB. The empty square represents the cost obtained by a naive no-indicator policy that always accesses the cache first, and in case of a cache miss, accesses the memory. The cyan rectangle shows the cost obtained by CAB. Finally, the pink circle depicts the cost obtained by a theoretical optimal static configuration. This static configuration is known only in retrospect, and we found it using exhaustive brute force search over numerous optional configurations. The results show that for most settings, CAB reaches a cost that is only slightly higher than that of the theoretical optimal static configuration. Furthermore, in some cases, the dynamicity and self-adjusting nature of CAB allows him to obtain a lower cost than that of the optimal static configuration. To conclude, selecting advertisement strategy was an open problem in both research and practical systems. Due to the dynamic characteristic of cache traces, there is no one-fits-all good static configuration. Hence, we designed CAB algorithm, which is dynamic and self-adjusting. Our evaluation shows that CAB provides close to optimal results in various settings while complying with the bandwidth constraint. Finally, recall that CAB stands for Cache Indicators Advertisement with Bandwidth Constraint. Hello, my name is...
Interesting work and great talk, Itamar. Let's see if we have questions on the Slack channel, or else I can go ahead. Okay, so I was wondering if you can provide some sense of how big the Bloom filters are in your setup, or what is the typical size of Bloom filters in practical deployments, and can you also comment on the available bandwidth, because you also mentioned about use cases of 5G networks where I presume the bandwidth is not a problem, or is it's plentiful. Can you comment on those two parameters?
Yes, so we used a simple Bloom filter. Well, actually, it is counting Bloom filter, but that the cache uses locally. But for advertising, it's sufficient to advertise only a simple Bloom filter, which in which every counter is reduced to a single bit, whether the count is larger than 0 or not. And our analysis and our concept may be used also for other indicators. As for your other question, so sometimes the Bloom filter can be rather large because, for instance, there is a SECOM paper about Akamai's CDN, and they talk about Bloom filter size of tens of megabits. So for that size, even if you send a Bloom filter, sending the whole Bloom filter is rather large. And even if you think about sending only the delta updates, only the list of changes, so it'll just indicating a single change, you need a log of the size of the Bloom filter. And if you have some tens or hundreds of changes since the last update, this is already also rather large.
I see. Thank you. And let's see. I think the other question that I had was about, you mentioned that CAB adjusts the indicator size, specifically when the false positive rate increases, then you increase the Bloom filter size, for example. So does this mean you have to rehash some of the keys because you're now increasing the Bloom filter size? Probably you have more slots now. What is the cost there, and how does this affect the performance in some way?
Yes, so actually of course the changes are, although the algorithm is dynamic, we make these changes only once in a while. It should adapt to changes either in the caching policy or in the trace, but the changes are not too frequent. And we also, I don't remember the exact numbers from the paper, but we talked about the overhead, and we showed that it is rather negligible with respect to the, if you have a large enough intervals, and currently the hashing can be done rather fast, and of course some of the work may be parallelized by using banks in the Bloom filters and the table and so on.
Okay, thank you. I think we have one question from the audience. If you can unmute yourself, and yeah, please go ahead.
Yeah, I have two comments. One is the weighted balancing of the false positives and false negatives really represents a kind of L1 norm of optimizing the average penalty. But in some cases, you may care about the likelihood of having to go to a distant server. It's kind of yes, no. So it's an example of a valid measure, but I would consider others as well. The other one is that it may be interesting to enter cache size into the equation. After all, it's also money, resource, energy, everything. And if the cache is larger, that's another way of having to go less to the remote server. So it's a trade-off. It's an add-on that you can stick onto this paper at that dimension, because you implicitly, I think, assume the given cache size, and under that, optimize the advertisement.
Yeah, so for the first one, you said, yes, you're right. Well, actually, even the method of equalizing the cost is a kind of intuitive way to reduce costs, but we don't have formal guarantee that this is the best way. So indeed, you may say that for me, false negative are much, much more important. Yeah. And as for your second comment, we actually don't assume anything about the cache size. The beautiful thing is that the algorithm adapts itself. It just counts the false negatives and the false positives, and adjusts itself.
Yes, of course, you don't assume, but indirectly, the cache is there, and the optimization is only on the advertisement. In principle, if you were planning a system, you could also try to optimize the cache size together with this. Again, it's just broadening the scope. It doesn't contradict anything in the paper, just adding a dimension.
Yeah, thanks.
Oh, I was on mute. I'm sorry. Yeah, I said thank you, Tamar, for the great talk and great questions from the audience. I think we are nearing the end of this session. After this, we have a 10-minute break. We'll be resuming at 9:40 Pacific time, which is 10 minutes from now. Thank you all.
Okay, so welcome back everyone for the last paper session of the conference. My name is Pratik Sharma and I will be the session chair of this potpourri session, which has two very exciting papers. So the first paper is going to be presented by Craig Mustard. The system is JumpGate, which is a system for data analytics with network connected acceleration. So Craig was a PhD student at UBC and he graduated recently and now is working in Oracle Labs. And now we can go ahead and watch and listen to his excellent talk video.
Hi, everyone. Thanks for tuning in. Today, I'm going to tell you about a project that shows how to integrate promising network-connected accelerators into data analytic systems. This is joint work with my colleagues from UBC, Swati, Nilu, Joel, Ivan, and Sasha. So first, let me introduce network-connected accelerators. In general, they can process data sent over the network. For instance, when data is loaded from storage to a compute cluster, there is opportunity to process it as it is being loaded, and researchers have shown this can be quite beneficial. There are programmable NICs called smart NICs, and Floam increased throughput of a streaming query 96% by offloading work to them. For programmable switches, NetXL, Diet, and Cheetah decreased runtime of join and aggregation queries by 2 to 8x, and Sonata reduced traffic by 1,000 times. There are also potential network-connected accelerators off the original data path. These come in the form of accelerator devices attached to the network like normal machines. For instance, devices such as network processing units, FPGAs, custom accelerator hardware, and even existing VMs optimized for packet processing. Instead of processing data transparently, we will need to coordinate data movement to use them. Even with off-path devices, we have seen software middle boxes speed up Hadoop operations by 4.5x. And so hopefully at this point, you're somewhat convinced that we could be using network processors to accelerate data analytics. But while prior work should promise, there are still significant barriers to adoption. On the left, I'm showing some examples of all the devices that we could potentially use as an NCA. And there are 3 general areas that still need to be addressed to make this all work. And no prior work has looked at these in depth. So the first issue is integration. Existing analytic systems provide a lot of feature and value to users, so it would be ideal if these existing systems could use NCAs. But these systems have execution models that are too complex. So we need to design a way for existing systems to use them. And we need to find a way for NCAs to read data stored in common analytics formats. Another issue is how to coordinate and manage multiple NCAs at the same time. Since each NCA might be very specialized, we want several to work together. For instance, software-based NCAs could read data in analytics formats and send it to programmable switches. Lastly, NCAs are tough to program because each might be specially designed hardware, and we need to design around these limitations. They're not like standard worker nodes that have lots of compute memory and storage. We also want to make sure that we get a lot of mileage out of each implementation because they can be hard to write. So overall, we need to solve these challenges to help integrate NCAs with existing analytics systems. So let's discuss the integration challenge. How should we add NCAs to existing systems? On the right are 3 analytic systems that could benefit from NCAs. One answer here is to integrate every NCA directly into every analytic system. This can be made to work, but it's not going to be a great solution. Specifically, when a new analytic system comes along, it will need to directly support all these devices. And when a new device comes along, all analytic systems will need to be updated. It will also be harder to share good implementations of NCAs between systems. So while this might seem like a strawman argument, I want to point out this is exactly the situation we have today. The promising prior work on NCAs I talked about has done exactly this. And prior work manually integrated each NCA implementation into each analytics system. And often they write query-specific or data-specific code to make their prototypes work, and many even seem to orchestrate the execution of queries manually. So what we need is a service that can abstract away the specification and operation of the data processing task from which backend devices get used. And we call this network processing as a service. Compiling one abstract program to different backends is nothing new. This is similar to what data processing systems and even general compilers already do. But here we are proposing to provide such an abstraction as a service to multiple analytics clients. And this paper is about the design of a prototype MPAS, which we'll talk about shortly. So compared to the prior approach, the advantages to network processing as a service are that we can abstract away device-specific management from the client system, so it's easier to use new NCAs. Existing systems will only need to be modified once to use the MPAS system, and new NCAs and new client analytic systems can be added independently, helping us get the most mileage out of NCAs. So now I want to introduce you to a prototype system called JumpGate. JumpGate sits between client analytics systems and implementations of analytics operations on NCAs. In a nutshell, JumpGate handles the idiosyncrasies of each NCA so the client doesn't have to. And JumpGate overall makes a few contributions. First, JumpGate provides a data flow interface to clients, and we show that this API makes it easy for existing systems to use JumpGate. JumpGate executes requests by compiling them to a novel execution model that is needed to support limited NCAs. And third, JumpGate contributes backend interfaces to simplify controlling and adding new NCAs because they are hard enough to program. And lastly, in addition to these design contributions, we evaluate JumpGate and the overall behavior of how analytics queries behave when using NCAs. While we did not have access to hardware accelerators for all operations, we used software-based NCAs to help fill in the gaps. So now I want to walk you through an example execution of JumpGate so that you can see how a query is executed. First, the user submits a SQL query to Apache Spark. I won't get too deep into exactly what this query does, but it basically breaks down the total sales of all items by state. So next, this query is submitted, Spark transforms it into a query plan, an internal representation of the analytics systems use. At this point, if we were just using Spark, it would simply execute this query plan on its worker nodes. But when Spark uses JumpGate, it splits the query plan into two, one plan for JumpGate and one plan for Spark's own workers. In this case, Spark decides to send almost all the query to JumpGate aside from the final aggregation. And then lastly, Spark submits the plan to JumpGate. What's key to understand here is that JumpGate requests are formed from the client's existing query plan. JumpGate provides a data flow API very similar to existing query plans of existing systems. And so now we're going to look at how JumpGate internally processes this request. So when the request is received, JumpGate maps the client request to a set of relational operations that run on NCAs. JumpGate has a library of relational operations. In this example, JumpGate has 3 NCA implementations in the library. JumpGate uses an API called the operator interface to detect when it can use an NCA. Developers implement this interface to inspect requested operations to tell JumpGate if a given NCA can be used. So JumpGate breaks apart the incoming request and searches for applicable NCAs. So JumpGate maps the request to 2 instances of the scan implementation. These scan operations translate data from existing storage formats to the JumpGate internal format, which we'll talk about in a second. Then JumpGate picks 1 instance of the join implementation and 1 instance of the partial aggregation. At the end of this phase, JumpGate knows which NCAs will be used to execute the client request. After figuring out the right set of NCAs, JumpGate coordinates them to execute and send data to one another at the right time. Recall when I mentioned that existing execution models are too complex for NCAs? The reason is that existing systems require all nodes to locally buffer data they produce, but this won't work for NCAs that have limited storage. To solve this, JumpGate schedules NCA execution as a staged network pipeline. JumpGate organizes NCAs into stages so that only NCAs that implement joins must store data, and the rest can simply receive and forward data to the next NCA. Staging is relatively simple, but it's required to enable NCAs with limited storage to work for analytics. In the example, JumpGate computes 2 stages because NCA 3 includes a join operation. The first stage builds the hash table used for the join. The next stage probes the hash table to emit join records to Spark. The next challenge is that NCAs can be limited in the complexity and amount of data they can read per packet. So NCAs need simple data formats they can operate on. JumpGate introduces a data format called network tuple formats, or NTF. NTFs are simple and query-specific data formats that NCAs communicate in. Before execution, JumpGate automatically computes the byte layout of the NTFs, and it compiles or configures NCAs to process those specific formats. To show you how these things work together, let's walk through an example. So first, JumpGate executes stage 1, which runs NCA 1 and NCA 3, building the hash table in NCA 3. When NCA 1 runs, it reads data from storage, converts it to NTF format, and sends it to NCA 3. And here I'm showing you the NTF format. The NTF contains 2 fields, both 64-bit integers, and a null vector with 1 bit per field. This is a really simple format, and that's the point. Prior analytics systems have used more complex formats, but we need simplicity here to enable the use of NCAs. So next, stage 2 executes, which runs NCAs 2, 3, and 4, which then sends data back to Spark workers. In this stage, each pair of NCAs exchanges data in a different format. So overall here, I've shown you how JumpGate orchestrates NCA execution and communication. Staged network pipelines and network tuple formats are part of the new execution paradigm that are needed to use NCAs for data analytics. So JumpGate's final design contributions are backend interfaces that help add NCAs to JumpGate. The details are in the paper, but in general, these interfaces allow NCA designers to tell JumpGate if it should use their device and allow JumpGate to coordinate NCAs to work together without NCAs needing to know about one another. One thing I want to underscore is that JumpGate only controls how NCAs connect to each other and when they start working. Data itself is exchanged directly between pipelines of NCAs. This means JumpGate is off the critical data path and NCAs can operate at full speed. So here are some of the evaluation questions answered in the paper. I'll be overviewing a few of them. We're going to look at ease of integration, overheads, how clients benefit from using systems like JumpGate, and when NCAs can accelerate queries and why. The big disclaimer here is that we did not have access to all the hardware that we needed to create hardware NCAs for most analytics operations. Instead, we mainly rely on software NCAs. These are real NCAs and they behave similarly to hardware ones, but they're just not as fast. So this allowed us to study the behavior of pipelines of NCAs before hardware was available. This paper looks at when speedup does and doesn't happen and explains why to motivate future hardware designs. So for a brief methodology, I won't go over details, but I want to highlight the client system and workload we use. For client system, we use Apache Spark, a popular analytics system. For workload, we use the TBCDS benchmark, an industry standard SQL benchmark that we run using an off-the-shelf benchmarking tool for Apache Spark. So first, how easy is it to use JumpGate? It took about 2,200 lines of code for Spark to make Spark be a JumpGate client. Relative to the 100,000 lines of code for all of Spark SQL support, this is only 2% extra code. With these changes, Spark can automatically offload about 60% of all operations from TBCDS and creates overall about 850 jobs for JumpGate. We were also able to add NCAs to JumpGate in 200 to 600 lines of code. Details on everything we implemented are in the paper. Prior work in this area only tested 9 queries and only supports a final filtering operation. JumpGate's Dataflow API let us offload many more operations, starting at the scan from storage, which is where the bulk of the data processing lies. So let's look at overhead. What we did here was run TBCDS with practically no data, so we only measure system overhead. We found that JumpGate has high startup overhead, on average about 3 seconds per query, up to 6 seconds. This is because the current version compiles and deploys many software-based NCAs for each query. We can reduce these overheads, but they're not a significant issue because systems like JumpGate will process lots of data, and so it will be worth paying the startup overhead. Also, we can simply not submit short jobs to JumpGate. On the other hand, there's low execution overhead. We found it took between 13 and 70 milliseconds for JumpGate to perform signaling for NCAs to switch stages. This means JumpGate can stay out of the way of NCAs processing data. In comparison, Spark takes between 11 and 950 milliseconds for the same test. So aside from startup overhead, our execution overhead can be lower than Spark. And overall, this shows how well the design of JumpGate works as a control plane. It sets up NCAs to work directly with one another so it can get out of the way and support high throughput NCAs. So now I want to show you briefly how NCAs behave when executing a real query. So this chart shows the behavior of JumpGate and NCAs running a job offloaded from TBCDS query 3. This is a good example of how queries work and also illustrates the main factors at play to answer our final 2 evaluation questions. Time goes from left to right. The timeline bars at the top show the breakdown of JumpGate setup and execution time. There's only one job executing here, and that takes 5 seconds to set up. The lower bars show each NCA used to execute the query. The red arrows show which NCAs send to which. So for example, we see the top 2 NCA parsers send to a join NCA, which sends to aggregation NCAs lower down, and the bottom NCA transmits to Spark. On each bar, we show a breakdown of where time went. The orange shows the fraction of time each NCA spent processing data. The blue shows the fraction of time the NCA was reading from or writing to the network. In reality, these 2 phases are highly interleaved, but we aggregate them here to show overall time. The speed up or slowdown is shown at the top. Here, JumpGate and Spark performance are very similar. I want to point out 3 things. So since a pipeline's throughput is limited by its slowest part, we can see the pipeline bottleneck is ORC2, the top NCA bar. In this case, the orange portion is the time to parse the ORC file plus the time to convert it to NTF to send on the network. The small amount of blue shows that it does not spend much time waiting to send data, but other NCAs spend most of their time waiting for data. Next, this chart shows how much data is transmitted between NCAs. This shows that as data moves down to the final NCA, the volume of data decreases a lot, often by many orders of magnitude. This is illustrated by the inset bar chart on the right. The left bar shows that there was 27 gigs of compressed ORC data read from storage. The middle bar shows this data uncompressed into 76 gigabytes of data in memory that needed to be processed. And together, these two bars show the data read and overall work performed by the analytics task. Without JumpGate, Spark would need to process this volume of data. But when Spark offloads this task to JumpGate, the rightmost bar shows the volume of data Spark receives. This shows that a system like JumpGate can significantly reduce work for the client system. This also shows why we chose to offload operations starting with reads from storage, because the bulk of data processing is done by operations closer to storage, and so they are good candidates for acceleration. This example illustrates the answers to the last two evaluation questions. What are the benefits to the client, and when can NCAs accelerate queries? The main benefit is to the client is a large reduction in data sent to the client system. This paper looked at data reduction trend for all queries in TBCDS, and we found 94% of TBCDS queries see a reduction in data transmitted to Spark, and about half see a reduction greater than 22x. This data reduction happens because NCAs are used to process that volume of data in the network. And we found that the amount of data put on the network is on par with what gets materialized in memory in a classic analytic system. Overall, queries will see a speed up, and that amount of data can be processed more quickly by NCAs. I don't have time to delve into all our results that we included in the paper, but overall, our evaluation found that format conversion was a common bottleneck, indicating that future work could accelerate format conversion. In the paper, there's a full analysis of TBCDS and an example using a programmable switch. So thanks for listening. In conclusion, I showed you JumpGate, the first prototype system to offer network processing as a service. I built JumpGate in order to research how to integrate existing analytic systems with NCAs and to identify future challenges. The design makes several contributions. It shows how to easily integrate existing analytic systems with NCAs. It introduces a novel execution paradigm to use NCAs and make them work together, and it contributes simple interfaces to add new and diverse NCA implementations. So thanks for listening, and I'm happy to take questions.
Okay, thank you, Craig, for the talk. I think if people have questions, they can post them on Slack or raise their hands on Zoom, and we'll unmute them. So while it looks like we're getting a question, while that is being posted, I think one pressing question I had was in terms of what the hardware support, right, for these operators. Where is the bottleneck there in terms of, is the hardware not ready or not available or easy to program with? Or if you can comment on the current and the future state of sort of network programmable hardware for this data analytics, that would be great.
Yeah, that's a good question. So right now we know of implementations that work for some joins, that work for filtering, that work for aggregation. They don't necessarily support every single operation on every single data type that you might want in a real query system. But there's currently enough to show that, like, yeah, this could work, and that they would be effective at speeding things up. So I felt like this was a good time to sort of do this work, because it would say, hey, we can do this system, so maybe we should start building more fulsome operations. Like a good example would be, maybe we want to do floating point operations in the network, or maybe we want to increase the amount of memory that they had, and things like that.
I see. But so you mentioned in the talk this notion of, you gave this compiler analogy, right? Wherein there's this common intermediate format. So what would be a good common intermediate format for NCAs?
So what we internally use is basically the data flow graph we get from the analytics client. And that has so far been a good intermediate format. I think that if there were commonalities between several NCAs, such that they had a different intermediate format, like you want to target like, P4 switches with LVMIR. I don't know that if we can do that, but that would be an example of a place where we could add another intermediate format. It's possible in the future that, say we have multiple NCAs that all have the same intermediate format. Well, JumpGate could target just the intermediate format and deploy to all those different NCAs as well.
All right. So we have a question on Slack, which is, can we treat GPUs like NCA? So suppose you want to implement aggregation on a GPU, which is one of the workers. Could you treat that as a NCA, and would that be a good idea?
Great. So the key things that I see as if something can be an NCA or not is if it can send and receive quickly on the network. if you can build a GPU implementation that can do that, that would be great. But my understanding of GPUs is that they're kind of built for large bulk operations and not sort of for streaming throughput. So that could potentially be a challenge with GPUs, but I know that there's work in an area that looks at improving that. So yeah.
Right. And, what are your thoughts on the sort of data format conversion between, the CPU memory and the custom format that you use, the NTF, right? So where is that going? Do you think that conversion is going to be a bottleneck for future architectures, or can we get some zero copy techniques?
Yeah, I think that it depends on the architecture that we want to use and how it can receive data over the network. I've seen some really interesting work that looks at how you can deliver network packets directly to the registers of a CPU, which is a very interesting idea to think about. But in general, I think the format conversion discussion will be ongoing, right? Like often with databases, you want to work in a columnar format. And the format I showed in the paper and the presentation here is not a columnar format, but in the future it could be. I think the sort of overall point to take away is that like we can decide the format at query submission time. So if we want to make a new format, we're not stuck with the old format that we decided on a few years ago. We can just add a new one for that specific query for those specific devices.
Wow, yeah, that would be pretty cool.
Yeah.
Okay, any more questions? Let me just quickly check. Okay, if not, we can sort of thank Craig again for the great talk and the very insightful answers that he has. And I'm sure some more discussions can go on in the Slack after the talk. So thank you again.
Thanks, everybody.
Okay, so our next talk is going to be on LIRS2, which is an improvement on LIRS, the cache eviction, the sort of well-known cache eviction algorithm. The talk is going to be presented by Professor Song Jiang from the University of Texas at Arlington. And now let us watch the talk video.
Hello, everyone. In this talk, I'm going to present a new replacement algorithm, LIRS2, which is an improvement of LIRS replacement algorithm. This is Song Jiang. This is joint work with my students, Chen and Xing Shen. We are from the Department of Computer Science and Engineering in University of Texas, Arlington. One of the major computer science technologies is the construction of memory storage hierarchy with the aim of achieving the speed of the fastest level and having the capacity of the largest level. To achieve the goal, caching is a key technique which leverages access locality to identify hard blocks and keep them in the cache. A replacement algorithm plays a critical role on caching efficacy. It works by exploiting locality for predicting future access events. There has been a large number of replacement algorithms proposed over the years. Among them, LIRS stands out with a consistently high hit ratio and low cost, with its unique way of characterization access locality. LIRS has generated a substantial impact in academia and the IT industry since its release about 20 years ago. The papers on the algorithm and its variant, ClockPro, has been widely cited. It has been incorporated in some real systems, including MySQL, NetBSD, and InfiniSpan. Obviously, we would like to identify blocks of strong locality for caching and replace blocks of weak locality quickly out of the cache. Therefore, every replacement algorithm has its defined locality measure to quantify its strength. How this locality measure is defined is a key to high hit ratio. LIRS high hit ratio is attributed to its uniquely defined locality measure, the reuse distance, which I will discuss further. Let's first take a look at the theoretically optimal locality measure, which is used by the OPT algorithm. OPT selects a block whose next access will occur fastest in the future for replacement. In this example block access sequence, block A has been accessed for a number of times. Assume this is the current time, and this block A has its last access, the second to last access, and the next access. And OPT's locality measure is the time distance from the current time to its next access time, tnext. A block of the smallest tnext has the strongest locality, and a block of the largest tnext has the weakest locality and the replacement candidate. As OPT has been proved to be the optimal algorithm, tnext is the optimal locality measure. However, this tnext measure is not available online. So now let's see an online locality measure. The LRU algorithm selects a block whose last access occurred farthest in the past for replacement. So its locality measure is actually recency, which is a time from its last access to the current time, tlast. So it attempts to use tlast to estimate tnext, which is not available online. There are two issues with the LRU locality measure. The first one is faithfulness. LRU's tlast measure contradicts OPT's tnext. With new block accesses, the current time moves forward and the tlast becomes larger and the tnext becomes smaller. So the estimation is wrong. The second issue is on steadiness. LRU's tlast measure keeps changing with new accesses, causing misleading locality characterization and confusing replacement algorithm. Let's use an example to see the performance impact of the faithfulness issue. Here we have a number of blocks that repeatedly accessed the scan access pattern. With the increase of the cache size, the misratio curve of LRU does not decrease, and there is a big gap between the curve of LRU and the curve of OPT. And the LRS addressed this issue with its uniquely defined locality measure. Now let's see how LRS locality measure helps with its faithfulness. LRS introduced the concept of reuse distance. It is a time distance between two consecutive accesses of the block. It refers to the most recent one by default. To keep its locality measure up to date, LRS actually uses the larger of the t-reuse and the tlast as its locality measure. Instead of estimating OPT's locality measure, the locality measure of LRS, t-LRS, is used to define cold and hot blocks. And it's assumed that cold blocks are going to be cold and hot blocks continue to be hot. Now let's see the scan access pattern again. With its locality measure to distinguish cold and hot blocks, LRS can consistently choose cold blocks for replacement and not be misled by small tlast with recently accessed cold blocks. And we can see that its misratio is as good as OPT's. Regarding the steadiness issue, people usually introduce the deeper access history into locality measure to reflect a block's longer-term access behavior. The LRU2 algorithm is such an example. It uses the distance from the second to the last access to the current time, which is tlast equal to t-reuse and tlast as its locality measure. And the t-reuse is more stable than tlast. And this tlast2 is actually take a longer and thus more stable history into account, right? So it's supposed to be more stable. However, because this tlast2 is a sum of these two locality measures, so the impact of tlast on tlast2's variability is still significant. Another major issue with LRU2 is it is much more expensive than LRU. It is not a big O1 algorithm. LRS locality measure is more stable than LRU's. However, LRS may also have its steadiness issue. LRS mostly use reuse distance, t-reuse, to determine if a block is either hot or cold. And it's assumed consistency of t-reuse to make the prediction. It's assumed that a small t-reuse is going to be followed by another small T reuse. A significantly varying T reuse can compromise its performance. However, we do see in some workloads, T reuse may change substantially. Let's take a look at this zigzag access pattern. In this access pattern, an ordered list of blocks are repeatedly accessed in alternate directions. Every small reuse distance is followed by a large reuse distance, which is again followed by a small reuse distance. This basically is against the assumption of lerth. And accordingly, we see this miss ratio is actually much worse than OPT. To address the issue, we naturally come up with the idea of using the sum of two consecutive reuse distances as a locality measure, which helps cancel momentary variations of individual ones. So this T2 reuse, which is the sum of T reuse 1 and T reuse 2, the two most recent reuse distance, it is assumed that there is a consistency between these locality measures, and this T2 reuse is going to be used to separate blocks into hot and cold status. And we propose the lerth2 algorithms. This lerth2 algorithm locality measure is actually defined as the larger one of T2 reuse and T last 2 to responsively track recent access events, similarly like what is done for LRU. Now the challenge is how to efficiently incorporate the new locality measure in a replacement algorithm. We know that the time complexity of LRU is big O 1. After adopting a more complicated locality measure, which is T reuse plus T last in LRU2, its time cost become big O log n. N is the number of blocks in a cache. And now we have a more complicated locality measure for lerth2. Can we still make the lerth2 as efficient as LRU with its big O1 time cost? To understand lerth2, let's first compare the design principles of LRU and lerth2. LRU uses an always trust strategy. In LRU, every block is trusted as a potentially hot one, and the block is then cached until not accessed for a long time. So in this way, even a cold block may stay in the cache for a long time before it is replaced. And the lerth2 is different. lerth2 uses a check and trust strategy. A block is checked on its access to decide its hot and cold status according to its T2 reuse locality measure. And only blocks trusted to be hot are cached, and cold blocks will be admitted into the cache but will be replaced quickly. Now let me use an example to illustrate operations in lerth2. We use an LRU stack to track up to two most recent accesses of a block, named instance 1 and instance 2. Assume there is a block access sequence where block B is accessed multiple times. After first access of block B, B1, the first instance of block B, is pushed into the stack. After second access of B, a new instance 1 is pushed into the stack, and the original instance 1 becomes instance 2. And in this way, we can efficiently track the first reuse distance and second reuse distance of this block. And we assume initially all blocks are hot blocks. Let's continue with this example. In lerth2, all hot blocks are resident in the cache, and only a small number of recently accessed cold blocks are in the cache, and they're going to be replaced quickly. And the lowest instance 2 of a hot block is always sit at the bottom of the stack to serve as a benchmark. A block whose instance 2 is in the stack when it is accessed becomes a hot block because its locality measure is smaller than that of the max block. If the block is not accessed for some time, its B2 is out of the stack. It becomes a cold block and be replaced. And if this block is accessed again and it's become resident again, but it's still a cold block because at the time it is accessed, its B2 is not in the stack. After some time, this block is replaced because it is a cold block. And if this block accessed again, this block becomes a hot block. And the reason is at the time it is accessed, its B2 is smaller than it's in the stack. So it actually produces a smaller locality measure and be promoted. In the evaluation, we use a diverse set of real-world traces. This includes 106 virtual disk traces from Cloud Physics, 4 traces from Microsoft Research, 5 I/O traces from UMass Trace repository. We choose result of 2 traces to present here. In one trace, LIRS2 perform much better than LIRS and other online algorithms in this ratio. To see the reason, we also plot CDF curves of variations of reuse distance and 2 reuse distance. And we can see that this 2 reuse distance has much smaller variation than 1 reuse distance, indicating that LIRS2 use a more stable locality measure. In the second trace, LIRS2 perform only a slightly better than LIRS. This is consistent to the observation on the locality measure variation distribution curves. While T reuse already have small variations, there is little room for LIRS2 to improve. Here are some takeaway messages. General-purpose replacement algorithms still have room for further improvement. If we choose to use a more history-rich locality measure, the efficiency of the algorithm should not be compromised. The LIRS2 give an example of such effort. Hello everyone. In this talk, I'm going to present.
Okay, so that was great talk. So we have Chen here who's going to answer questions. Yeah, as always, please post them on Slack or raise your hands on Zoom. So while we wait, I had a couple of questions. So let me get started with that. So I really like the idea of having, the most recent reuse distance plus the penultimate reuse distance and adding them together. So I was wondering, why stop at 2? And did you explore going back further in an object's access history? And would, let's say, LIRS3 be any different than LIRS2?
Oh, yeah, I think that this is kind of a trade-off. If we use two reuse distance and even 3 or 4 reuse distance, the time overhead will be increased. So I think except we use 1 reuse distance, 2 is more better, I think. Okay. And there are also another research like LRU2, and they also used it's kind of like look 2 times before current access. Yeah.
Right. Yeah, it makes perfect analogy. So the other thing, just to expand on what you touched upon, the sort of computational overhead of keeping these extra reuse distances and computing the eviction priorities. How much is that computing overhead compared to something very simple like LRU?
Oh, for LIRS2, with only a few instructions for updating pointers and the block status upon an access, they are efficient as ARU because folders to every block access up to 3 operations. That is the same as ARU. Like when a new block access, we put the block to the top of the stack, and maybe there will be a second operations, like, and we remove the instance 2 from the stack. Yeah.
Okay.
It's almost the same as the ARU. So we confirm that it is the O1 ton complexity.
Nice. Yeah, great. It seems extremely versatile and general, and look forward to using it.
Yeah.
Any more questions? Looks like we are also out of time. So let's thank Jen again for answering the questions. And with that, we can sort of close the session. There's a break, and there's a third keynote by Kim Keaton starting in about 10 minutes. So
No. So sorry, Pratik. Like there's no break. We're actually sort of like going right into the keynote.
All right. Sorry, I misread the schedule. All right.
Yeah, I mean the schedule is different on each day, so understandable.
Yeah.
All right. Hi, folks. It's my pleasure to welcome you to the final keynote of SYSTOR and to introduce Dr. Kimberly Keaton. Kim has multiple decades of research experience in developing database management systems and working on emerging sort of like hardware technologies. Recently, she's been focused on persistent memory and disaggregated systems. And she has lots of like patents due to her work over these decades. She has contributed to HP's SYSTOR and Express Query products. And she served as co-chair for like all the major system conferences, like OSDI, Eurosys, Sigmatrix, FAS, DSM, PS, and so on. So it's an honor to have you for a keynote. Thank you, Kim, and please take it away.
Thanks, Vijay. Just wanted to check you can hear me okay and see the slides okay?
Yes.
Yes, great. Well, I'm delighted to be here today to have a continuation of the discussion that we started yesterday with Sasha's keynote around memory disaggregation. And the work that I'm going to talk about today is done in collaboration with my former colleagues at HPE, as well as collaborators at VMware Research and Microsoft Research, UT Austin, and ETH Zurich. We're living in a world today that has lots and lots of data. There are more and more devices that are producing more and more data. We want to be able to analyze that data so that we can make decisions, and increasingly to automate those decisions. So we need answers very, very quickly. And the urgency with which we need these answers really points towards wanting to analyze data that's memory resident. But of course, there's a challenge there because as the data gets bigger, it's harder and harder to make sure that that data can remain memory resident. At the same time, the system balance isn't really keeping up. Our processor's ability to compute over data is outpacing their ability to actually access the data in the first place. So lest you think these are new issues to be grappled with, the thumbnails that you see on the right-hand part of the slide here are from talks that I've given like 4+ years ago. So these challenges have been with us for quite some time. They're likely to continue to be with us until we can address them. So what can we do about them? Well, one interesting new development over the last few years, in addition to new memory technologies, is that networking technologies are getting faster. So I think about things like RDMA, as well as emerging interconnect standards like Gen Z and CXL. And so these kinds of interconnects are providing us with tens to hundreds of gigabytes per second of bandwidth. They're also providing sub-microsecond latencies. In addition, they provide a feature called one-sided access, which is essentially, it allows a processor on one side of an interconnect to access read and write data on the far side of the interconnect without requiring a processor to be involved on that far side. These capabilities are really allowing us to think outside the box, both literally and figuratively, when it comes to how we want to design our systems. And in particular, we've seen a fair bit of work over the last few years in new system organizations that take advantage of remote memory and disaggregated memory. So what do I mean by those terms? By a remote memory architecture, I mean an architecture where compute nodes are actually sharing some of their memory with their fellow compute nodes. And there's been quite a bit of exploration of this space, in part because these architectures are easy to build with commodity off-the-shelf parts. And in particular, we've seen this general architecture applied to paging kinds of workloads, as well as cache line-based accesses and runtimes to support that to overcome some of the amplification issues associated with dealing with pages. We've also seen remote memory being used for partitioned global address space architectures, distributed shared memory architectures, exposed through memory mapped file interfaces, and even used as a setting for doing offloading of application kernels. So there's quite a bit of work in this space. Another alternative view of how to take advantage of new memory technologies and networking technologies is through a disaggregated architecture. And here, the idea is that compute nodes are accessing memory that's distinct from the compute node memory. So there's a pool of memory that's being accessed across the interconnect. Now, this pool of disaggregated memory may or may not have computational abilities associated with it. So it may be active if it does, passive if it doesn't. This type of an architecture is also being explored quite a bit in the last decade or so, again, with paging kinds of devices and applications in mind, as well as exposed through memory interfaces, key value stores, file systems, as well as database storage engines, even as data structures. And so there are quite a variety of different APIs that we're seeing disaggregated memory exposed through. In addition, we're starting to see work to design operating systems for disaggregated architectures. So for the rest of the talk, I'm going to focus my attention on this type of a disaggregated architecture. These kinds of architectures have quite a few benefits. And so first and foremost, they allow an application to have access to a higher memory capacity than will fit into a single machine. So this is kind of what some of the initial motivating sort of issues that I was describing. They bring other benefits, though, as well. They allow independent scaling of the different types of resources in the system. So if you want to add more memory into the system, you can merely add more memory to the disaggregated pool. You don't have to add another compute node in order to get the memory that's associated with that compute node, even if you don't need the processor. They also provide separate failure domains between different parts of the system. So if a compute node dies, as long as it's published its state into the disaggregated pool, another compute node can actually take over the computation for the failed node. And we'll see an example of that later in the talk. And then finally, because disaggregated memory is equidistant from all of the compute nodes, it might provide us the opportunity to do better shareability of data between the different compute nodes. So disaggregation is not a new idea. As we saw in Sasha's talk, disaggregation has also been applied quite a bit to storage architectures. In fact, a lot of the cloud providers today, this is pretty much the way that they've architected their systems. What's new here is that we're applying disaggregation to memory architectures. So just to give you a sense of how a disaggregated memory architecture might work, I can tell you a little bit more about a system that I'm familiar with, the machine at HPE. So the machine was a hardware-software co-design program where we built a large hardware prototype that had 160 terabytes of disaggregated memory that was accessed by compute nodes over a photonic interconnect that was running an early version of the Gen Z protocols. In addition to this hardware prototyping effort, we also built a software stack, including low-level software all the way up through the applications, just to see what kind of applications could take advantage of this type of an architecture. What we found was some pretty interesting results. I mean, there's quite a range of different possibilities in how one might take advantage of a large pool of disaggregated memory. And we saw performance improvements ranging from about an order of magnitude of speed up for modifying existing frameworks like Spark, all the way up through 3 or 4 orders of magnitude performance improvement if you were willing to rethink how you structured an application. In this particular case, the financial modeling use case was one where you're trying to predict the value of a portfolio of investments. And that involves a lot of Monte Carlo simulations. And so if you can actually pre-calculate the results of some of those simulations ahead of time, you can actually then store those results in a really large lookup table and turn what would have been a computational problem into a lookup problem and achieve huge speedups as a result of that. So really impressive performance improvements are possible through this kind of a memory-driven architecture. It's not without its challenges, though. And we heard about some of those yesterday, and I want to talk about some more of those today. Even though the networks are getting faster, the latencies of accessing memory across an interconnect are still about an order of magnitude slower than what we would see if we were trying to access the local or near memory. So much so that we've started calling these disaggregated memory farm memory in contrast to the near memory in the local nodes. So that's one thing that we need to be able to address. Another challenge is that hardware support for coherently sharing data inside of this architecture is really only provided inside of a single compute node. If I want to share data between compute nodes, it's up to the designer of the system to figure out how to do that in a coherent and consistent fashion. And then finally, because we're accessing data across the network, that means we're going to be transferring the data across the network. And so as we know, data movement is an expensive operation, and it might not even be necessary depending on what you're trying to do with the data. So all of these challenges are interesting ones that we want to explore, and I'm going to spend the rest of the time in the talk talking about some potential ideas for addressing these challenges. Additionally, I'm going to talk about how we might be able to exploit the fact that disaggregated architectures provide separate failure domains to improve the application resilience. And then finally, if there's time, we'll talk about some interesting areas for future research. All right, challenge number one, the elephant in the room. Network latencies really dominate the access time for disaggregated data. Now, programmers typically access memory using data structures. So let's reframe this problem and ask how we would design data structures for a disaggregated memory environment. In particular, how can we design a data structure that can take advantage of the huge pool of disaggregated memory, but do it in a performant way? And so my colleagues and I explored this question in a HotOS 19 paper, where we looked at what we were calling far memory data structures. So the basic idea, the ingredients of a good far memory data structure are storing the canonical version of the data structure in the far memory to take advantage of its huge capacity. Now, clients of the data structure are going to be able to cache portions of the data structure that they're working on in their near memory. That's to provide performance benefits there. And the way we were thinking about this was it would be a data structure specific cache that would go away when the application exited. So it's an ephemeral cache. The final part of the recipe is an algorithm for how you operate on the data structure. And so here, the idea is that we want to be able to access the data that's in the far memory as well as manage the cache contents in the near memory. And we wanted to be as general purpose as possible. So we didn't want to make any assumptions about there being a processor in the far memory. So we want to see how far we can get with just using the hardware primitives that the interconnect and the memory system itself will provide. And we'll see how far we can get with that. In order to overcome the disparity in performance between far memory and near memory, we're going to need to have data structure operations that can complete in a constant number of far memory accesses, ideally just one far memory access if we can swing it. So in order to do that, we're going to need to trade far memory accesses for near memory accesses by being really intelligent about how we optimize pointer chasing kinds of operations, being smart about how we're actually caching the data in the near memory, and then also thinking about how we want to efficiently support sharing of the data between the different compute nodes. Clever data structure design will get us part of the way there, but if we want to get to that goal of just a single round trip per data structure operation, we're probably going to need a little bit more support than the existing hardware provides. So part of this paper was also then exploring what are some simple hardware extensions that we might be able to add in order to better be able to build far memory data structures. The first example that we looked at was indirect addressing. So here, fairly straightforward idea, we want the ability to essentially dereference a pointer in a single far memory operation. So that might be dereferencing a pointer the way we see on the left-hand side of the slide. We might add an offset to the pointer before we dereference it, or we might dereference it and then add an offset as you see on the right-hand side of the slide. So all of these different addressing modes make sense in this kind of an environment. And they actually make sense for read operations, for write operations, even for simple arithmetic operations. Even more powerful, we can combine those. So for example, doing something like fetch and add indirect so that we can dereference the pointer and then increment the pointer, which is very commonly used by programmers. So this kind of indirect addressing and these types of operations are very, very useful for optimizing pointer chasing in pointer-rich data structures. So this is one really key building block of our ability to deliver those far memory data structures in good performance. If we want to maximize our usage of that single round trip to the far memory, another way to do that is to access multiple addresses in that single round trip, something that the high performance computing community calls scatter and gather kinds of operations. So here I've shown 4 different kinds of scatter and gather operations, depending on whether we're reading or writing data from far memory and whether the addresses that we're reading from or writing to are contiguous or discontiguous. So for example, read gather on the left-hand side of the slide is reading data from far memory, from discontiguous addresses in far memory, and gathering them into a contiguous buffer in the near memory. These kinds of operations are really, really helpful if we're trying to do strided access to data structures. So for example, if I've got a matrix that's laid out in a row major fashion, I can use this to actually do column major accesses to that kind of a matrix data. So again, a very useful primitive for the hardware to provide. Already is provided in various forms of RDMA and Gen Z. So let's put together these hardware primitives with some clever data structure design and see how one might actually go about building a far memory data structure. Let's imagine that we want to build a large data structure, a map, for example, in far memory. So one option would be to use a tree, but there's potentially a lot of issues with doing pointer tracing in order to traverse the tree. So a tree is maybe not the right data structure by itself. Similarly, we can imagine using a hash table. Well, there, if you end up having to resize the hash table, you have to reorder and reorganize the entire data structure. So a hash table on its own is probably not the right choice either. But if we combine those two ideas, we come up with something that's much more interesting. And in particular, we explored something called an HT tree or hash table tree in the HotOS paper. And so the idea is that the data structure is a tree where the leaf nodes of the tree are hash tables. And so that's the canonical data structure that's stored in far memory. In near memory, the data structure clients are then going to cache the upper portion of this data structure, the tree part of the data structure. And because it's not, the entire data structure isn't a tree, this upper part of the data structure is relatively compact and will fit inside of the near memory of a compute node. When the compute node wants to access data, it'll use that locally cached tree to navigate to the appropriate hash table, compute the hash function to figure out which bucket it's going to, and then use the indirect support in order to actually retrieve the data that it cares about, all in one far memory operation. So common case, we're able to achieve that one far memory request per data structure operation. In the event that we do need to reorganize the hash table that's being accessed, and what's nice about this type of a data structure is that that's a much more localized access and reorganization than having to reorganize the entire data structure, which would be very disruptive. So this is just one example of a data structure that can be designed using some of these simple hardware extensions so that we can actually get good performance and still take advantage of the really, really large memory capacity of a disaggregated pool. So by now you're probably thinking, what happens when multiple of those clients want to cache the same data? It's a great question. It's our next challenge. In particular, let's think about a case where nodes 1 and n both want to cache part of the red data structure shown here on the slide. Now, if node 1 actually makes an update to that data structure and writes it back to the far memory, there's no built-in hardware support for node n to know that there was a change. So node n's data that's cached is now stale, and there's no way for it to know without periodically polling to understand whether there have been any updates to the data that's stored in far memory. So this is definitely a challenge, and there are a couple of different ways that we might be able to address this challenge. One might be to accelerate notification of updates. And we've seen some work in the literature on a system called Concordia, for example, that uses smart switches to do this. We had another idea in the HotOS paper, which I'll tell you about on the next slide. Another idea is to eliminate the need for these notifications at all by designing the system in such a way that you can avoid the need for coherence. So let's talk about these two ideas. First of all, rather than having to repeatedly probe from a client in order to understand whether there are updates, it would be much more efficient if we could have a callback that would be triggered only when there is an update. So imagine that you could define a region of memory that you were interested in watching. And then anytime there was an update to that region, you would receive an update or a notification to the local compute node that would allow it to then invalidate the stale copy that was cached in its local memory. So that's certainly one way that you could use this. If you could have a small enough region, you might even include the updated data in the notification that's sent. So then you could even use that to update the locally cached copy. So these are great. So this is one way that this kind of a notification mechanism could help us to manage the cached contents. It gets even more interesting if you're willing to be more specific about what kinds of values and what kinds of changes that you're looking for. So for example, if you are able to understand when a counter would count down to 0 or when a lock value is released, this would provide a fairly powerful building block for building coordination primitives to allow computations on different nodes to coordinate with one another. So the same kind of mechanism can be used in a variety of different ways. So this is one idea for how you might be able to accelerate notifications to support data sharing between nodes. But it really only represents, it assumes that the data is shared. It only represents one point along a very broad spectrum of different sharing alternatives. And so with collaborators at UT Austin and VMware and HPE, I've been looking at another point on that spectrum, something that we've been calling disaggregated partitioning. And here the idea is that even though all of the data in the disaggregated memory may be physically visible to all of the compute nodes, we want to logically partition ownership of parts of the data set to different compute nodes. So for example, here in the graphic, compute node 1 owns partitions D1, D2, and D5. So what that means is that compute node 1 is responsible for reads and writes to those partitions. What this gives us the opportunity to do now is that compute 1, the owner node, can actually pretty aggressively cache the contents of the partition in its local memory without worrying that any other compute node is going to make an update that would invalidate the locally cached copy at the owner. So if the owner can cache as much as it wants to without having to do any extra work to ensure that that cache is up to date, this is potentially going to provide us with high performance in the common case. In the event that we have to repartition or reconfigure the system, say, for example, because one of the compute nodes dies, that's pretty easy, actually, with disaggregated partitioning. All you have to do is reassign the ownership to another node. If the original owner is still alive, you have to make sure that any locally stored updates are flushed to the disaggregated memory, but then it's really just a matter of reassigning the ownership. We don't need to reorganize the underlying data that's in the disaggregated memory because, again, it's all visible to all of the compute nodes. So this is a relatively lightweight mechanism that we can use in the event of a failure of the compute node, in the event that we want to increase or decrease the number of compute nodes, or even potentially if we want to handle load imbalances due to skewed workload patterns. We've built a sample key value store that employs disaggregated partitioning. It's called DP store. And it uses consistent hashing to assign the ownership between the different compute nodes. And because there's exclusive ownership, those compute nodes are able to decide how they want to manage their cache. They can either cache shortcut pointers to the key value data, or they can actually cache the data in the key value pair itself. And that allows them to satisfy requests without doing any far memory accesses. We're going to compare DP store with a system called Clover, which was published in Usenix ATC in 2020. Clover is a shared everything kind of key value store. So all of the different compute nodes can access all of the data. And because of that potential for sharing between compute nodes, the way that the data is stored is in a multi-version kind of a format. So there can be concurrent read-write sharing in this system, and it's supported by this multi-version data. As a result, because of the sharing, the nodes are going to really focus only on caching the key value pointers. And that will allow them to find the most up-to-date version of the data. So we're going to compare DP store against Clover, both for common case performance. And so we're going to use the YCSB workloads to do that. And so you see the different YCSB workloads and their read-write percentages on the x-axis of the graph here. On the y-axis, you see the throughput in million operations per second. So our setup here is that we've got one memory server and 8 compute nodes that are making requests of making the YCSB requests. What we find is that DP store outperforms Clover quite a bit, and that's due in large part to this exclusive ownership, allowing us to cache very aggressively. So recall I mentioned before that the DP store allows us to cache both shortcut pointers as well as values themselves. So some of the hits in the cache are actually not incurring any kind of a far memory access, which gives very, very high performance. In contrast, Clover has to do at least one round trip because at best it has a shortcut pointer to the most up-to-date value. If there are multiple values, there may actually be more round trips across the network in order to find that most up-to-date version. So this is really just a confirmation of our intuition that disaggregated partitioning is very, very useful in the common case. In the event that we have to reconfigure, we can also look at the performance of reconfiguration for DP store. Here we're using YCSB workload B, which is a read-dominated workload, in order to do that experiment. And we're going to simulate the failure and recovery of different compute nodes in our system. So at 5 minutes, we start with 4 compute nodes, and then at 5 minutes, we will remove 2 of the compute nodes in the system. At 10 minutes, we're going to add those 2 compute nodes back in, and we'll see how long it takes to recover. And as as our intuition suggested, DP store is actually very quickly able to accommodate any changes in the compute node counts. We see similar results for other YCSB workloads with either more read percentages or higher read percentages or lower read percentages as well. So this is just one example of how sort of stepping back and thinking about how you want to organize a system can allow us to sidestep some of the challenges of having to manually manage the coherence in a data sharing kind of an environment in a disaggregated architecture. Our third challenge is really around data movement. As we know, this is one of the fundamental truths of computer science. Data movement is expensive. It's expensive in terms of the time to transfer the data, the resulting cache pollution that might happen because you bring a lot of data into your memory hierarchy. It's also expensive in the amount of energy that's consumed. And there's a data point at a recent ASPLUS paper that really told us that over 60% of the overall energy in Google mobile applications is only because of data movement kinds of operations. So definitely very costly along many dimensions. It might not even be necessary. And so think about, the way that we design sometimes our data structures. For example, if we use inlining in a hash table where we put multiple values in the same block, and then we have to transfer the entire block in order to understand whether the data that we care about is there. We result in decisions that result in a lot of read or write amplification. So unnecessary data is being transferred just because of the design decisions that we've made. Sometimes actual applications are the purpose of the application is really to allow us to do filtering operations on the data to find what we care about. So for example, databases are very commonly used to apply predicate-based selection kind of criteria so that we can discard some of the data and only get back what we care about. So there's definitely lots of different examples of how more data may be transferred than is strictly necessary. Wouldn't it be great if the memory system could help us to minimize the amount of unnecessary data transfers? And in particular, some of the work that we've been looking at is, how can smart disaggregated memory actually help to limit data movement? Smart both in the sense of the semantic abstraction that the memory provides, as well as the computational abilities that are required in order to achieve that desired semantics. So in particular, this is work that I've been doing with folks at HPE as well as ETH Zurich. And we've been thinking about, rather than a memory kind of an interface, let's treat disaggregated memory as a set of data collections where the application will access the data collection as a unit. And this is a nice match for a lot of the data science applications that are increasingly popular today. And we're going to borrow an idea from the database world, that of a view. And so the application is going to see a logical view of the data that may or may not be the same as the underlying physical representation of how the data is stored in the memory system. These views are going to be provided by operators, and similar to some of the talks that we heard earlier this morning, that can be applied in line by the smart disaggregated memory as part of a data path operation. And so in order to have this work as a bump on the wire in an inline fashion, we really need to focus on operators that are stateless or minimally stateful, the ones that don't really generate a lot of intermediate results that need to be managed. Similarly, it makes more sense to think about predefined functions rather than user-defined functions, because we want to avoid having to deal with arbitrary, potentially buggy or even malicious code, and also avoid having to deal with code that has large computational or memory requirements. So definitely possible to have predefined functions that are stateless or minimally stateful that can be applied in an inline fashion here. Now the question is just, what should those functions be? Looking across a wide range of different application areas, data analytics, high performance computing, machine learning, there really are a fairly standard set of kinds of operations that make sense here and that are common across these different areas. They fall roughly into three categories: filtering, transformations, addressing kinds of operations. So in the filtering space, database selection, style predicate selection, that sort of thing, regular expression matching, we'll see variable numeric precision as an example that's increasingly popular in machine learning. On the transformation side, we have things like compression and aggregation that will reduce the amount of data that's being sent. There are also interesting kinds of transformations that keep the data the same size but provide other additional helpful properties like encryption to improve our security story. And then finally, with smart addressing, we're going beyond the strided accesses that we saw earlier into more general purpose transformations, things like matrix transpositions that are really just about how we address the data in a clever way. So we've been exploring this using an FPGA-based SmartNIC and being able to then implement the different operators in the FPGA so that it can operate as a bump on the wire as data is read or written to and from the memory that is associated with the system. The way that this is exposed to the programmer is through extended RDMA verbs. And so there's basically a verb to implement the operator logic that's then invoked by the programmer. We've prototyped this general setup in a system that we call FAR-View because it's providing views into FAR memory. And the way that the system works is that the FPGA is divided into different regions, where each region implements the logic for an operator or a set of operators that correspond to a user's request. The regions can be dynamically reconfigured so that we can actually then support different kinds of requests over time. The implementation also includes a networking stack as well as a memory stack for accessing and managing the memory in the FPGA. We're going to compare our FAR-View prototype against a compute node baseline that is an Intel-based platform that has a ConnectX-5 NIC from NVIDIA. Now we've implemented all of the different classes of operators that I mentioned on the previous slide, but since our challenge here is really to eliminate or minimize data movement, I'm going to focus on the filtering results. In particular, our first example is going to be predicate selection, like we would find in a database application. Basic idea is we're reading data from a table, and then we're going to apply the predicate to select only a subset of that data. And that's the selectivity, which is shown in the different columns of the table here. Our baseline configuration, we're going to read all of the data from the table into the compute node and then apply the filtering on the compute node. For the FAR-View system, we have an operator that's implemented in FAR-View that's going to apply the predicate at the memory and then only send the selected data across the network. So what we see is if we look at the performance for doing 100 selections, we find that pushing the filtering closer to where the data lives is actually very effective, especially as the selectivity increases and we're discarding more and more of the data. A second example is reducing numeric precision. Again, a common operation in machine learning kinds of applications. So here our goal is to read 1,000 8-byte elements and then return them with a reduced precision, anywhere from 1 byte to up to 8 bytes. And again, the baseline is we're going to read all of the data from the memory into the local compute node and reduce the precision at the compute node. FAR-View is going to reduce the precision on the memory node and only return the desired bits. What we see is precision is shown on the x-axis, and then the time for reading these 1,000 elements is shown on the y-axis. So for the full precision read at 8 bytes precision, we see that the commercial NIC does outperform our FAR-View prototype, which isn't optimized. But as we start reducing the precision, there's quite a bit of performance improvement that FAR-View can provide. So these are just a handful of examples of the kinds of operators that might make sense in a smart disaggregated memory environment. There are lots more, and both from a data sort of management kind of perspective as well as an application level perspective. And I think this is potentially, like several other areas, an interesting area for future work. Our final space is in the opportunities that disaggregated memory will provide for us, and in particular, the separate failure domains. So recall that in a disaggregated memory architecture, there's really kind of a partial failure model here. So compute nodes may fail independently from the disaggregated memory system. So long as the state that the compute node was operating on has been published to the disaggregated memory, it's possible for another compute node to take over for a failed compute node. And this is a pretty powerful thing when we think about how we might design resilient applications for disaggregated memory. The kinds of applications that do well in a disaggregated memory environment are ones that have really, really large working sets, potentially very long-lived working sets. And they're not very amenable to traditional kinds of fault tolerance techniques like checkpointing. So the ability to selectively restart individual tasks is a very attractive thing when we think about how these applications might be made more resilient. It's a topic that we explored when I was at HPE in a system that we called Memory-Oriented Distributed Computing, or MODSI. MODSI is a framework for writing resilient applications in disaggregated memory systems. And it basically provides fine-grained recoverability without requiring explicit checkpoints. And it does that by exploiting a task-based programming model. So applications are written as a set of tasks, which are then scheduled by an underlying runtime system. And the runtime system will then take care of rescheduling any tasks that fail. The runtime is written executed in a decentralized way that takes advantage of the disaggregated memory to capture the global state of the system, both the application's state as well as the global state of the runtime itself. Now, I should say that the assumption that we made about the system in the MODSI work is somewhat different than the assumption that we were making in the FARView work. In MODSI, we're not assuming a smart disaggregated memory. We're really assuming just the bare bones ability to do one-sided operations and atomic operations and so on. So that's what we're going to work with here. The interesting thing is that we're able to use the disaggregated memory to capture the global state of the computation. We don't have to create the illusion of global state. We can actually have data structures that represent that global state in disaggregated memory. We'll use our one-sided operations as well as lock-free programming techniques to operate on those shared data structures in a fault-tolerant way. So let's dive into some of the details of this system to understand how it works. We'll start by talking about the programming model. Now, again, this is a fairly standard set of task-based programming model types of ideas. Applications are designed as a set of tasks, where a task is a function that's applied on a data input to produce a data output. In this example, or in this system, we're assuming that those inputs and outputs are resident in the disaggregated memory. Tasks need to be idempotent so that when you execute them again, regardless of where you're executing them, they're going to provide the same outputs, provided that you've given them the same inputs. There may be dependencies between tasks, either data dependencies because the output of one task is the input of another one, or control dependencies because all of the tasks in a particular set of tasks need to execute before any of the tasks in a dependent set of tasks. So in order to capture these control dependencies, we use an abstraction of a job, which is the set of tasks that need to execute in its entirety. We don't need to know what the task execution graph looks like a priori. It's possible for the execution graph to be formed dynamically because tasks can actually generate other tasks and can create new tasks. So we can discover what the dependency graph looks like over time, which is really useful for both recursive as well as iterative kinds of applications if you don't necessarily know what the stopping criteria are ahead of time. Application programmers are going to define the granularity of the tasks based on the logic of the application, as well as the need to be able to do that fine-grained recovery. So just to look at a quick example, we'll use a PageRank as a running case study throughout the MODSI part of the talk here. So if we boil down PageRank into a set of numeric calculations, it's an iterative algorithm where in each iteration, we're going to do a sparse matrix vector multiplication, where the matrix represents a graph. And so basic way that can be mapped onto our MODSI programming model is that for each iteration, we'll create a job. And then within that job, there will be a set of tasks executing parts of our sparse matrix vector multiplication, or SPMV. If we draw that graphically, here we can start by having an iteration that corresponds to our first, a job that corresponds to our first iteration in blue. The solid colored boxes are the parent task, if you will, of the particular job. Now that parent PageRank function is going to be able to create the smaller SPMV tasks, which are shown as the hollow squares. It'll also create a new job that corresponds to the next iteration and populate that with the initial task for that iteration. That's the solid red box that you see here. Once we start executing the tasks, the SPMV tasks may discover that they've been assigned quite a bit of work and may choose to further decompose the work that they've been assigned into additional tasks. And we see that in the graph that's dynamically being formed as we see the execution beginning. So all of the tasks in job 1 in blue will execute and complete before any of the tasks in red for job 2 are going to start for iteration number 2, and so on and so forth. So each iteration will proceed independently, and then it'll precede its subsequent iterations. So that's how the application is written. Underlying all of this is a runtime that is responsible for quite a few things. I don't have time to talk about all of it, but I want to just focus on the scheduling related functionality that the runtime system provides. And in particular, that's the ability to track control and data dependencies, to execute tasks once the dependencies have been met, and then restart any tasks that fail along the way. So the way that MODSI does this is that it will have a per application pool of workers that's executing tasks on the different compute nodes. And this is a pool is instantiated at the application invocation time. And the way that the workers coordinate with one another is through a set of shared data structures in the disaggregated memory. So here we see a couple of examples for dependency tracking, scheduling, as well as failure detection. And we'll see more of the details of the first two on subsequent slides. The way that execution proceeds is in a very implicit and decentralized kind of a fashion. A parent task begins execution. It will create its children tasks, and gradually those will be scheduled as their dependencies are met. And it's all done using this set of shared data structures in disaggregated memory and the workers on the compute nodes. The runtime system itself is written in a fault-tolerant way using lock-free programming, and it's exposed to programmers through a library interface. Now, a very key role of the runtime system is to enforce dependencies. So one example of those dependencies is the control dependencies. So again, reviewing, that's all of the jobs tasks need to complete before any dependent jobs can then begin their execution. So in a centralized kind of a scheduling environment, this would be fairly straightforward. The scheduler would know when all of the tasks had completed. But since we don't have a centralized scheduler, we need to be able to figure this out in a decentralized fashion. So the way that we do that is that the workers that are executing the tasks of a job have to reach a consensus that they're all done. Essentially, this is basically a barrier of the execution. We need to get to the point where all of the work for a particular job is completed before any subsequent work can begin. Now, as you know, barriers are often very, very brittle to failures. So if one of the workers dies while everyone else is waiting at the barrier, there's going to be a very, very long wait involved. So we don't want to use a traditional barrier. Instead, for ModC, we adapt the idea of a barrier into what we call a dynamic group barrier. So like a traditional barrier, it allows all of the members to reach a particular point in the execution before they proceed. But unlike a traditional barrier, it does allow the membership to change over time, hence the dynamic part of the name. So the basic idea is that when a worker finishes executing its tasks, it's going to wait on the barrier until either everyone else finishes and the barrier is released successfully, or until a failure is detected. And then all of the waiting members are going to fall out of the barrier and look for any remaining work to be done that might not have been finished by the failed worker. The way that this gets implemented is using a set of shared data structures in the disaggregated memory, and you see them on the right-hand side of the slide. The first part of the data structure is a participant vector, where each participant in the barrier has a slot, indicating that it's alive. The other data structure is a collection of counters, essentially one counter that corresponds to changes in membership, another that corresponds to how many members are currently waiting on the barrier, and then a final counter that indicates the barrier had been successfully released. All of these counters are packed into a 128-bit word so that we can operate on them all together in an atomic fashion using a 128-bit compare and swap atomic operation. The way that the barrier works essentially is when a worker arrives at the barrier, it will count the number of active participants in the participant vector. It'll increment the number of members that are waiting. And if it's the last one to arrive at the barrier, it'll actually release the barrier all in one atomic operation. If it's not the last member, it'll wait on the barrier for further instructions by continuously reading the counters to understand whether there are any changes. If a worker discovers that another worker has failed, then it has a couple of things that it needs to do. It needs to both mark the failed worker as no longer a participant in the vector, and then it also needs to increment the membership changes counter in order to signal to the other workers that are waiting. So the workers that are waiting on the barrier and notice that there has been a change in the membership counter, they know that there was a failure, and then they have to drop out of the barrier and actually look for that additional work to be done. So this is just one example of how a relatively simple set of data structures in shared memory can be used to actually indicate, and provide the building block for a fairly complex coordination kind of mechanism. Once all of the dependencies have been met, a task is ready to be executed. And the way that the workers execute those tasks is relying on a set of per worker work queues in the disaggregated memory. You can see them here. So each element of the work queue is a pointer to a task descriptor that's also stored in the disaggregated memory. The task descriptor really indicates interesting information like the status of the task and what job that it corresponds to and other things. In order for us to ensure exactly once execution, we introduce just one other data structure, a slot that holds the descriptor for the running task that the worker was last working on. In order to actually schedule the work, a worker will optimistically copy the task pointer into its running task slot and increment the worker owner, the work stealing owner pointer in order to consume the task from the queue. It'll then try to change the status of the task to running from ready. And it'll do that using an atomic operation. If it's successful, it'll then begin executing the function and we're off to the races. If it's successful at executing the function, then upon completion, it will change the status of the task to finished. Now, some workers may work faster than others or have more work assigned to them than others. And so in order to prevent a straggler kind of a situation, we design these work queues in such a way that they're double-ended queues, in particular lock-free double-ended queues. And so the owner worker is going to access one side of the queue and other idle workers are going to be able to steal work from the other side of the queue. Unless you're worried about whether it's possible for two workers to try and execute the same task at the same time, rest assured that doesn't happen because only one of the workers is going to be successful in changing the status of the task in the task descriptor. In the event that a worker fails, this same work stealing mechanism can be used to allow us to have the remaining workers execute the work that had been assigned to the failed worker. We can also even steal the task that was in the running task slot. And there's no worry about restarting execution of that failed task because we'll get the same result regardless of where we run the task because the tasks are idempotent. We've built all of these mechanisms in a prototype, as well as a fair bit of memory management kind of functionality, additional data structures, concurrent lock-free data structures, as well as additional mechanisms that take advantage of those data structures to provide things like failure detection and so on. We'll use this MODSI prototype in our evaluation. We'll compare the MODSI implementation of PageRank against a more traditional implementation of PageRank that's written using MPI barriers for coordination and using checkpoints every 3 or 4 iterations for fault tolerance. We're going to make this as comparable a comparison as possible. We're going to use the same data access mechanisms between the MODSI implementation and the MPI implementation. Our experimental platform is a large scale-up machine, the HPE Superdome, that has 16 NUMA nodes. And we're going to treat one of the NUMA nodes as the disaggregated memory, and then the rest of the compute nodes are going to be, the rest of the NUMA nodes are going to be treated as compute nodes in the simulated environment. First question is, how sensitive is MODSI to the task size? We're going to evaluate this by actually looking at actually measuring the execution time for different task sizes. So here, PageRank, we're going to execute that over a 64 million vertex synthetic graph. So 64 million rows in our matrix. And we measure the execution time for task sizes of 1,000 rows all the way up to 8 million rows. And you see that in the x-axis in a log scale. The y-axis shows the relative execution time relative to the best case scenario, which we've measured to be 15,000 rows per task. What we see is that there's a very, very large range of task sizes where we achieve within 5% of that optimal value. So between 5,000 rows to up to 100,000 rows per task, all within 5% of the optimal values. So really, really small tasks, there's definitely some scheduling overhead. Really, really big tasks, there's not as much of an opportunity to deal with work stealing because the things you're stealing are quite big. But even with those really, really large tasks, we're still able to achieve within 17% of the overall optimal. So answer to the question is that MODSI is able to achieve very good performance for a wide range of different task sizes. If we think about the fault tolerance of the system, here we're going to execute PageRank for 10 iterations, and we're going to inject a failure at some point along that execution. And the point that we do that is shown on the x-axis on the graph. The y-axis is the execution time to get all 10 of those iterations completed, including any recovery work that has to happen along the way. We're going to do this so that we have always a constant number of workers. So we'll inject our failure, and then we'll immediately introduce a new worker so that there's always a constant number, 14 workers in the experiment. We'll start by looking at the failure-free execution. So MODSI is shown in yellow. The failure-free MPI execution without checkpoints is shown in orange. And we see that those two are pretty close. So, we did the right thing in terms of trying to, to ensure that we had the same kind of data access mechanisms that we were using. Once we introduce checkpointing every 4 iterations, we see that there's about a 10% degradation in performance, and that's shown in the green line here. When we start introducing failures, we see that the overall execution time of the MPI workload really depends on when the failure was injected relative to when the last checkpoint occurred. And so you see that by the sawtooth pattern in the blue line here. So if it's been a long time since the last checkpoint, we have to roll back to that checkpoint and then do a lot of rework in order to get to the point where the failure occurred. So that can result in up to 35% slowdown relative to the execution without any failures. Now, MODSI, in contrast, all we have to do is restart the failed task. So that only results in a 1% degradation relative to the failure-free execution time. It's shown in a gray line here, but it's hard to see because the gray line is pretty much behind the yellow line, which is the failure-free case. So overall, MODSI's ability to do very, very fine-grained recoverability provides us better performance than a checkpoint-based alternative. If we were doing checkpoints even less frequently, there would be even more benefit that we would see as a result of this experiment. So, whirlwind tour of a bunch of different interesting ideas for how one can overcome challenges and potentially exploit some of the interesting opportunities that are provided by disaggregated memory kinds of environments. It's really just scratching the surface, though, of all the interesting work that can be done in this space. And I think that there are a number of really interesting questions that remain, all up and down the stack. And so in particular, if we think about things like algorithms, there is this wonderful opportunity to rethink how we design algorithms for a disaggregated memory environment. We saw an interesting case where we could memoize results and turn things into a lookup problem. You could also imagine having really large indexes or using producer-consumer queues in disaggregated memory for communication. Maybe for machine learning operation or algorithms that don't require up-to-date data, you could even avoid having to worry about coherence issues. So all kinds of interesting possibilities there in terms of rethinking how we design algorithms. In the data structure space, I talked about one data structure that makes sense for disaggregated memory, but there are lots of others that we could also explore. It would also be interesting to figure out, are there general principles for designing data structures in a far memory environment? In the programming model space, I think there's probably lots of interesting things that we can learn from program analysis for right-sizing tasks. Also, there's interesting synergies that are potentially there between disaggregated architectures and new computational models like serverless computing. From a system software perspective, we borrowed some ideas from the concurrent programming field. There are undoubtedly other techniques that we could potentially use to improve the efficiency of what we're doing. So for example, MCS locks, which would forego really expensive operations for understanding whether there are updates and turn that into more local operations. Also, coordination-free data structures, for example, that might provide better scalability under highly contended workloads. Smart memory, we talked a lot about this yesterday in Sasha's keynote, and I think that there's a lot of really interesting possibilities here. She was focused more on application level code, and I talked about some data-centric operators in the far view part of this talk. But I think there are also interesting questions in more system level kinds of questions, and how smart memory could potentially allow us to improve the resilience for disaggregated memory, maybe implementing replication or erasure codes and so on, as well as potentially providing new guarantees like transactions or providing new capabilities like snapshots in memory. And then finally, there are some interesting questions about hardware-software co-design. What do we need from a smart NIC or from a memory device itself in order to support the kinds of ideas that we want to support for the rest of the stack? So again, all kinds of really interesting open questions to be explored for further work. So wrapping up, disaggregated memory really provides a number of different benefits for data-centric applications. It's not without its challenges, and hopefully I've given you at least a handful of ideas for how we might be able to address some of those challenges, and similarly, how we could go about exploiting some of the new opportunities that are provided with these architectures. think there's a lot of room for additional really interesting work. And I hope that I've piqued your interest and that I've encouraged you to join me in thinking outside the box for how disaggregated memory architectures can be made successful. With that, I'll conclude.
Thank you for the great keynote, Kim. I guess like Itzhak has a question. Go ahead.
Yeah, a question and a comment. The question is, I'm not sure whether you have a clear position on disaggregated in the sense of truly separate memory boxes, as opposed to having the memory with the compute nodes, but still accessible through the network, everything the same, except that you didn't separate it completely. Do you have a clear position on one versus the other, or doesn't really matter?
Yeah, I mean, I think both of them provide different benefits, right? So on the one hand, if you're exposing part of a compute node's memory, there's an advantage there because you don't have to add new resources in order to be able to use that. You can use the idle memory that we saw in Sasha's talk. You can expose that idle memory for use by other nodes. And so in that sense, it can help with an efficiency argument. My concern about that kind of an architecture, though, is that we lose our ability to independently scale the different resource pools. And then similarly, you're now trusting, your compute node is now trusting another compute node, which might have a computation that's running on it from a different tenant. And so I think that there are some interesting security challenges that crop up in what I was calling a remote memory environment that might not necessarily come up quite as much in a disaggregated memory environment, where you're able to—
This was my second question, security.
Yeah.
And I'm not sure after all, you don't really mind if someone touches your processor, you mind if they touch your data.
Right.
And the fact that the data is kind of in no man's land doesn't necessarily secure it.
Right. So there are, I don't know if you've looked at, like the Gen Z spec or the CXL spec. There are facilities that are being provided in some of these new interconnects to, essentially have zone-based protection so that you can restrict access to certain parts of the memory system to particular compute nodes. So there are mechanisms that can interconnect, potentially, sort of capability style ideas, for looking at accessing parts of the memory system as well, and as well as encryption and things like that. So I think that there are a number of tools in our toolbox that can help us, to protect the data in the disaggregated memory, from a malicious actors.
Until you attend a security conference and they show you that nothing works.
Yes, and so I should maybe attend some more security conferences because I haven't had that wonderful experience. So
yeah, I mean, it's a question of, first of all, who and what you trust.
Right.
Seriously.
Yeah.
And these days, it's really not clear.
Right.
Third parties, who works for whom.
Right.
And side channels on top of everything.
Right. And so, so there's still unanswered questions, right? So we still need to figure out what is the set of techniques that's going to make sense here. And because we're talking about memory speeds, the techniques that worked for storage, not necessarily going to work for memory. And so I think that there's an opportunity to do some interesting work here.
Yeah. And the final question, I didn't hear the word power or energy. Transporting data across the interconnect, even when most of it could have been accessed locally, that burns energy.
Right. Yeah,
it's not
totally
just
agree. Yeah, exactly. And so, so I did mention the word energy, I think, and power at least once. And but none of the evaluations really included that. And so that's a fair point. But I agree with you. It's not just performance, it's also energy related, power related. And so that's all the more reason for us to find ways of minimizing unnecessary data movements. And so that's why I think if we have at least some degree of intelligence in the memory system, that might be able to help with that.
Thank you.
So, hi, Kim. Thanks for your talk. It was really, really interesting. So I spent a lot of time thinking about how latency sensitive we might have to design applications with extra latency from the far memory. So I was wondering, like, if you've seen what techniques you've used in your work and related work to mitigate that. Yeah, as a start.
Yeah, and so I think there's starting to be a lot of interesting work in this space. Much of what I've seen for designing data structures in it's mostly a remote memory kind of a space, has looked at having a fair bit of processing capability on the far side. So for example, like the AIFM work that was at, I'm going to get this wrong, at OSDI, I think, in 2020, as well as some of the ACM NVM work from ASPLOS in 2020. They both assume that there's a fair bit of computational ability on the remote side. So you can then combine one-sided accesses where appropriate with two-sided accesses. So for example, for things like memory allocation and whatnot. So if you've got the ability to mix and match those different kinds of accesses as possible, that seems like it's a fairly effective way of doing things. If you know enough about the data structure so that you can prefetch the data that you care about before you need to use it, that's also a win, because you're really, you're trying to avoid being stalled while you're waiting for this far memory latency operation, right? If you can cache things locally and find a way of doing that in such a way that you don't incur too many coherence-related overheads, that's also another good technique for doing these kinds of things.
Do you see applications overlap, like a request to remote memory with local compute?
And I think that so that kind of goes back to like grappa style sort of work where we're issuing a bunch of different operations, and then we're going to do stuff locally, while we wait for those operations to come back. So I think that that's also a useful technique if your application can tolerate that kind of overlapping of those operations. Be curious to talk with you about some of the techniques that you're seeing as effective in that space as well.
Yeah, I've done some work in this space, so it's interesting to talk about that.
Great.
All right, we have one more question from Joe. Unfortunately dropped out. Oh, there he is. All right.
Hi, Kim. It's you gave me a lot to think about with
excellent.
All this disaggregated stuff. So I have a question about one of the last comments that you made about using erasure codes with remote persistent memory. It's also something that I've thought about a bit, but I get a lot of pushback saying, what are you going to have, like a network partition, or are you going to lose the node completely? And especially if you have your compute and your memory on the same node, you're going to lose a lot more than just your memory. So could you expand a bit more on how you're thinking of it?
So this goes back to the earlier question that Yitzhak asked, do you want to have a lot of, computational capability on those nodes? And so, maybe this is one of those cases where you want just enough to be able to do the redundancy kind of calculations that you care about, not necessarily, you don't want to lose your ability to, to do application level computations. So that might be, something, a reason that would sort of tip you more in favor of disaggregated architectures rather than remote memory architectures. But in terms of of network partitions and other kinds of issues of losing part of the memory space, so there I think it really is making sure that there's that there's a wide enough sort of stripe, if you will, of sort of partitions that you can choose from, such that they're even in the event of a network partition, that you have the opportunity to still have appropriate numbers of shares in order to be able to recalculate and reconstruct the data that you care about. That may or may not be possible given the way that the fault domains are set up in in the environment that we look at. So I think within a local area, you might not be able to do something where you can survive the failure of that local area. You might need to combine this technique within the local area, because you're talking about the latencies that are going to make sense on memory timescales. Combine these techniques with something else that would get us sort of a resilience to the failure of the local environment. So maybe there's an application level replication strategy that you can use to write a copy to a remote location. So I think it's probably not a one size fits all. There's probably a combination of different techniques that we are going to need in order to survive increasingly large sort of types of blast radiuses.
All right, thanks.
All right. With that, we'll wrap up. You can ask further questions to Kim on the Slack channel. And Kim, thank you so much for the great keynote. You'll learn a lot to think about. All right. With that, this concludes actually like SYSTOR for this year. Thank you again for all of the authors who gave great work, and all of the keynote speakers. And with that, I'd actually hand it over to Dalit to talk about SYSTOR for next year.
Thank you, Vijay. Bruno, can you bring up the slides, please? The few slides of the closing remark. Or should I do that?
Sure, just to look for them quickly.
Okay.
If you have them open.
Just a minute.
Okay, I think I have them here.
Sorry.
Just share. Okay.
So good afternoon, good morning, and hi everyone. I'm Dalit Naor, and I'm here talking on behalf of the SYSTOR's steering committee. Can you flip and thank you. So I'll just take 2-3 more minutes before we adjourn. First of all, to thank the organizers of SYSTOR 2021. I know how much work it is, especially now with, with doing it all remotely. Amazing effort. So thank you, everyone. Thank you, the program chairs, Vijay and Dani, who have been here all 3 days and selected a great program. And thank you, the general chairs, Bruno and Michal from IBM. Everything went so smoothly. And again, I know how much work it is, so great work. And we also had the supporting team of the other responsibilities. We had Idan from Red Hat, who did the posters, Joel Nider from UBC, who did the publication chair, Michal Friedman from the Technion, who was the publicity chair. And of course, as usual, we had Eti, who helped us with the arrangement. And those who know SYSTOR know that there is no SYSTOR without the Eti. So a big round of applause to everyone. And let's go now, Bruno, to next year. So I'm happy to announce SYSTOR 2022. This will be the 15th conference, and it will take place next year, almost at the same date, June 13th to 15th, Monday to Wednesday. And hopefully, let's keep our fingers crossed, on site in the Haifa site auditorium. We did benefit. We had now 2 SYSTORs in a row that were remote. Definitely there were some benefits. For example, this year we had many more papers, people, very diverse people from across the globe, great keynote speakers that we were able to attract. However, I think we're tired of this and we all want to get together like we used to do it many years ago. So let's hope that next year we'll all meet together in the auditorium as before. And in the next slides, we already have an organization structure to SYSTOR 2022. We have Frank Belosa from the Karlsruhe Institute of Technology in Germany, and Moshe Miki Gable from Toronto, who will be the program chairs, who agreed to be the program chairs. Thank you very much. We're looking forward to work closely with you. And we have Hillel Kolodner from IBM and Michal, who will continue to do it next year as well from IBM, who will do the general chairs. And I hope that by having Michal twice, 2 years in a row, it will help with the information transfer and will maybe make life easier. So again, thank you for those who agreed to be on the organization team for 2022. And my last comment, if you can, Bruno, is that later tonight or tomorrow, you'll get an email requesting to fill out a survey. This is something that we've been doing over the last 5 years, I think, and it's very useful. We always read it, collect the information, try to improve, try to come up with new ideas. So please fill out the survey when you get the email. So let me again conclude. Thank everyone. Thank the attendees as well. And I hope we all, the steering committee, we all hope to see you physically, at least some of you, next year in SYSTOR 2022. Thank you very much. And this concludes SYSTOR for this year.